tell me when to start, and I'll be happy to do that.
In live stream, yeah. Okay.
Give me 10 seconds. And
no, take your time, Chika. It's okay.
Yeah.
I will only speak a few minutes.
Yeah. Oh, okay. Okay. So that's fine. That's fine now. Yeah. Okay. So yeah, take it away.
Okay. So today we would like to start BCV Spin version 2021, and Professor Kaiser Shafi, one of the founders of BCV Spin, will give us an introduction to the school. Kaiser.
Thank you, PQ. Thank you very much. And thank you everyone for joining and preparing to participate. We hope it will be an exciting meeting. It's a pleasure to welcome you all to the first BCV Spin online meeting. And I'm delighted to be able to address friends and colleagues from around the world to this first Zoom meeting. While being online is an inaugural moment due to the ongoing pandemic, BCV Spin has a rich, as some of you may know, 30-year history. And let me just briefly summarize. So BCV Spin, as you probably know, is an acronym which denotes the countries Bangladesh, China, Vietnam. Vietnam was included in 2007, I believe. Sri Lanka, Pakistan, India, and Nepal. Now, BCV Spin was founded in 1989 with strong ICTP support. Very strong support, actually, because the director at that time was Abdul Salam, who, as you know, won the Nobel Prize with Glasgow and Weinberg in 1979. Now, Abdul Salam actually did attend the first school. And after some discussions, we had decided that the school should start off in Nepal, Kathmandu, being a neutral country, more neutral country, a beautiful country, not the most beautiful, I'm saying, among BCV Spin, but a beautiful country. And we thought this is where it should start. And he took part in the first school, where the then king of Nepal also invited us for a reception at his palace. And there are some pictures around which I can look for. This meeting, actually, when it started, was in high energy physics and cosmology, and also in condensed matter, evenly split between the two. And so I directed that school together with Jogesh Pati, who was a close collaborator of Abdul Salam, and also Yulu, who is now in China. For the first schools, at least, Yulu took part in the meetings. The original concept of BCV Spin was to allow young, talented scientists living in underserved regions to engage in research. And some 30 years ago, many of them did not have adequate opportunities for learning, collaboration, and career advancement. Of course, things have changed in the last several years, especially as far as China and India are concerned. And the other countries are making progress, and we really want to make sure that this impetus and this motivation continues, especially with all the young people who are willing to attend this meeting and help organize this meeting. So BCV Spin, I would say, is an early example of addressing educational and scientific inadequacies, as well as lack of diversity, and finding productive strategies to combat them. So the first school was held in 1989, as I mentioned, in Kathmandu, in two parts. There was even a school in Pune around, believe it was 1992. And at some point, this BCV Spin school came to an end, partly because of some political changes happening in Nepal, and also because we had a new director. Salam passed away in 1996, and we did have one school in 1997. I looked at the speakers. We had a distinguished list of speakers in that school also, including topics in string theory, physics beyond the standard model, inflation, cosmology, and all that. So fortunately, it turned out, with the help of colleagues in China, we restarted the BCV Spin School in 2007, actually. And then several schools were held in China, and also one in Vietnam, thanks to PQ in Hue in Vietnam. And in 2014, we even branched out to Mexico, actually. There was a school which was held in Mexico. We did plan a school, and the organizers who are here spent a fair amount of time looking at to organize a school in 2020 in China. But of course, because of COVID, we had to shelve the idea. So to conclude, I would say that we have entered the third phase of BCV Spin, and we have a terrific cadre of young, enthusiastic colleagues on the planning committee, which bodes well for a bright future of BCV Spin. The director of ICTP, Professor Atish Dabolkar, will join us at some point, hopefully today or during this period.
Hi,
And,
Kaiser, I'm here.
yeah. Oh, you are here. Oh, thank you. Yeah, good. So thank you, Atish, for joining. Yeah. Maybe then I would let Atish say a few words. But before concluding, I want to explicitly acknowledge all the speakers who have agreed to provide lectures. It requires a certain amount of commitment and dedication. So we are really grateful for that to all the speakers, and we will individually acknowledge them during the sessions. And also finally, last but not least, I want to acknowledge the co-organizers of this meeting. I actually, being a somewhat senior person, have taken a laid-back approach with these young Turks, especially really leading. I want to thank, in particular, Anil, Thapa, Anish, Goshal, Digesh Rao, Nobuchika, Noshin Shah, and Nobuchika Okada. PQ, of course, has been associated with BCV Spin from early on, even earlier than 2007. I don't remember, but we know that you started
2007, yes.
7, yeah.
Yes.
And then, of course, you organized a very important school in 2011 in Vietnam. And we are hoping that if COVID will come under control, we can move schools around a little bit and with various countries with your support. There is a plan to organize an in-person BCV Spin school in December of this year in Nepal. But we'll have to carefully watch the situation to make sure that this can be carried out safely. So without much ado, let me please request Dr. Professor Atish Dabolkar, the ICTP director, to address the audience. Thank you very much.
Okay, thank you very much, Kaiser. This is a great pleasure for me to be here for the opening of this BCV Spin school. As I understand, this was started, ICTP has a long connection with this because in 1989, started with Abdus Salam and our founding director, and then Jogesh Pati, Yulu, and Kaiser, as I understand. And I think to bring together future scientists from South and Southeast Asia region. The first one was in Kathmandu, and then since then we've had several in Nepal and in China, in India, Vietnam, Mexico also. All the best for the school. I'm very happy that this activity is continuing despite the COVID limitations. I can tell you that ICTP also successfully has been managing the COVID crisis. We managed to graduate our something like 100 students from all over the world coming to ICTP campus and completing their master's program successfully. And we celebrated the 30 years of this postgraduate master's with very nice talks by the Nobel laureate Andrea Ghez and the president of APS and so on. And it was a 3-day-long ceremony joined by again by alumni and ICTP well-wishers from all over the world. And one of the ideas that came up during that is to really consolidate and strengthen this network of ICTP associates and affiliates around the world, and to have regional chapters so that in each region there is a kind of a presence of ICTP is more organized way. And from that perspective, a school like BCV Spin is really perfect because it really brings together people from a region. And I think there is an opportunity to grow more in that direction. We are also trying to create a global, more a portal for ICTP, where these kinds of interactions between scientists connected to ICTP in different parts of the world and our activities at Trieste and elsewhere, it becomes easier. And hopefully in the coming year or two, we will have a more organized approach towards at least online connection, in addition to what we do in person. And so and ICTP's new strategic plan was also approved and by the Scientific Council. And some of these are the ideas for the future, to seek greater global cooperation, maybe fundraising for that purpose. And we are actively working on this. During the COVID emergency, normally ICTP has something like 5,000 scientists coming to ICTP every year. We could not, of course, bring people to Trieste campus, but I'm happy to report that we did successfully hold many of our conferences online, like BCVSPIN. And this year we had 8,000 participants. So in a way, the number of participants increased during the COVID time. So of course, there is nothing to replace an in-person contact, and I hope we are able to resume that. But I wish you all the best. I'm sure this is an excellent set of speakers. So all the best. Thank you.
Thank you, Atish. Yeah. So having heard a nice presentation from both Kayada and Atish, let's begin the first lecture of the school with Professor Naushin Shah, and she's going to lecture on standard model and Higgs physics. Thank you.
Hi. So let me see if I can share my screen properly. Do you guys see it?
Yes.
Okay. All right. So it's great to be here to talk about basically the standard model and the Higgs as the starting lecture for the BCV Spin school. And I hope, again, like we've talked about, that we can have these schools more regularly in person. That would be absolutely fantastic. But anyway, so to get started, so this will be a series of 2 lectures, and I'm going to start off talking about the standard model, and in particular, the role the Higgs plays in, symmetries, the idea of symmetries and symmetry breaking, etc. But the goal is going to be to understand and think about how do we go beyond the standard model, right? What do we need to do? Why we want to go beyond the standard model? And what are some of the basic ingredients that you would need to have in a theory where you go beyond the standard model? And in, obviously in 2 lectures, I will not be able to go through, all the super technical details and, in depth in either the standard model, the Higgs, or BSM. But the goal I have is to give you a more physical intuition and a global picture of what we are doing. And I hope that the interested student would then get motivation and direction in, various things that they can go and then look into. So I think that we have both the chat and also this Google form that's available for people to submit questions. And I think we're going to do questions at the end of the lecture. Yes. But so I think that either I think Digesh or Nobuchiko, you're going to be taking
Oh yeah, that's right. Yeah.
Well, somebody else is keeping an eye on the chat, because it's kind of hard to do if I'm, looking at my screen, so I don't see that. So if there are questions there, I'm hoping that one of you will interrupt me and ask. So in particular, okay, so most of the questions we'll leave for the end of the talk, but if there are questions about clarification, you don't understand the notation or something short, then I think those are questions that maybe should be brought up during the talk. Okay, so with that, let me get started. So, the first thing that we want to start off with is, when we're looking around us, what are the different forces that we see around us, right? So there's the four forces. So on the one hand, you have gravity, right? And we understand that as being basically an attractive force between any 2 massive objects, okay? Then the other most common one is electromagnetism. And again, we understand that as something which, particles have charge. You have particles which have opposite charge, they attract, and same charges repel. This is one of the major forces, between and within atoms, and is mediated by photons. Then we have the strong force, and this is the thing that is responsible for binding together protons and neutrons to form atomic nuclei. And we also know that protons and neutrons themselves are made up of more fundamental particles, which we call quarks. So here, this, for example, the proton is made up of 2 up and 1 down quark, etc. And these quarks are again bound together by the gluons, which are the mediators of the strong interaction. Then we have the weak force, and I, at least in my mind, kind of think about it a little bit differently than the other ones. It's something that actually mediates particle transformations. So an example of that is beta decay, which I have up here. So that's how a neutron basically converts to a proton while emitting an electron and a neutrino. And this happens via these massive gauge bosons, these W's and Z's. Okay, these are the things that mediate the weak force. And these are massive, unlike all of the other mediators that we've talked about for gravity, graviton, photons and gluons, which are massless. But these things these W's and Z's are not, they are massive. And this in fact makes it the weak force to be very short range. And an additional thing is that these W's and Z's, the W's are charged, electrically charged, whereas the Z's are not. Okay, so this is what we see right now when we look out into in nature, yeah? But what's the big picture we're trying to get at, right? So these are basically, I list here these forces as we once understood them. Now we know that the electricity and magnetism, they're the same thing, right? We understood that about 100 years ago, and that's electromagnetism. We also right now understand this, the unification of the electroweak force, right? The weak force and how that comes together with E&M. But at the same time, we don't actually understand why that happens. We know how it works, but not why, okay? But we also hope that there is, a bigger symmetry or bigger structure which governs all of these forces together, right? Something which joins together with a strong force, and somehow something happens with gravity also. And there is, at some high energy, the ultraviolet scale, the UV scale, where everything comes together in some sort of great theory of everything, right? But honestly, we really have no idea what could possibly be going on in this side of the picture. Again, we're kind of living over here and we want to get to somewhere here, okay? And apart from this picture that I have schematically drawn for you over here, there's also the question of dark matter, which I will not really address today, but it's something to keep in mind that this is not actually incorporated in the picture of the standard model, et cetera, that we will be discussing today. But must somehow, obviously, be added to the physics that we understand. All right. So with that, then, let's get started with looking at what is the standard model. Okay. So the first thing I want to point out is that the standard model is a completely empirical model that we have built up basically over the past 100 years. So what we know is that they are, it has a certain matter content, and there's certain symmetries that seem to govern this. So what is this? So here I have a picture of all of the fermions. So this is the matter content of the standard model that we understand. And here are the force carriers. So when I say generations, that's each column, okay, over here. And basically, if you were to ignore masses, these 3 columns are copies of each other, okay? And we don't have really any understanding of why that happens. Apart from that, there is, so these purple things up here, those are the things which are called quarks. Okay, these are the ones which feel the strong interaction, so are charged under the strong interaction, whereas the ones at the bottom, these are the leptons, and these do not. All right, so there are numbers on here, which I'm not sure if you can read them very well, but I'm sure you can look this up. And they have their charge assignments, their spin assignments, their mass assignments. And one thing to note is the difference in the masses in the 3 generations. So for example, the up quark is 2.2 MeV, okay? And the top quark is 173 GeV. That's basically 5 orders of magnitude between them in just the mass. But otherwise, these are exactly the same. And if you actually included the neutrinos, which we don't know what their masses really are, we just know that they are massive, they have a mass, you're probably adding another 5 orders of magnitude. So again, why? The other thing to note is actually, if you look at the universe around us, most of it is just pretty much just the first generation. I mean, your protons and neutrons are made up of just these 2 quarks up here, okay? And, pretty much everything else is electrons. I mean, that's what makes up atoms, molecules, etc., everything around us. So why in the world do we have these additional generations? We have no idea, right? I mean, that's a big question. Again, this is something that was empirically built from observation, right? It was observed that there are these additional particles, and was their charge assignments, masses, etc. And here we go. But we don't actually have an understanding. And again, nothing in here, addresses the question of dark matter. Okay. So what do we do? Well, what do we do with this, right? We've discovered all of these particles. How do we go beyond that? How do we actually do physics with this? So the first thing is the standard model Lagrangian. Okay, you have to write down what that is. So that is the thing which describes both the dynamics and the interactions of all of the different particle contents that we were just looking at. And what we basically write down is the minimal thing that we can. It has to include all of the fields that we observe and the necessary interactions that we observe. It needs to have respect unitarity and renormalizability, basically saying that, the physics that you get out of it must make sense, right? You don't want infinities, etc., things like that. And then what I have, put in bold here is symmetries. Okay, that, is a big part of what governs the type of interactions, etc., that we can write down in our Lagrangian. So what are these symmetries? So symmetries are basically transformations that you can do on your Lagrangian, which leave it invariant, right? So you do some operation on the fields transform in some way, but the physics doesn't change. So an example, so the things that we need to have is, 1, Lorentz symmetries. So those are space-time symmetries, right? You need to have physics here be the same as physics there, right? And physics today is the same as physics tomorrow. But you also, in addition, have what are called gauge or local symmetries. Okay, and that's this thing that I write down over here, SU3C cross SU2L cross U1Y. And I will go into in detail exactly what this means, but basically connecting to the forces we were talking about, this is the strong force, the SU3 color, that's what the C stands for. And this SU2 left cross U1Y, that is the weak and the electromagnetic. So technically this is the weak, and the U1 is hypercharged. That's what the little y is. And when you have these internal symmetry, as I'll try to show you, is that this actually demands the presence of gauge bosons. So if you have a Lagrangian which has certain types of symmetries, the local symmetries, then you need to have the presence of these gauge bosons, which we associate with the force carriers, the things that which mediates these forces in your theory. Okay, And not just, and it doesn't just demand the presence of these gauge bosons, but also dictates the kind of interactions that these gauge bosons have with all of the particle content, which is charged under any of these symmetries. You can also have accidental global symmetries. For example, if like you didn't have any of the masses in the fermions that I was showing you previously in the standard model, I told you that the three columns look exactly the same, then that would be a symmetry, a flavor symmetry for all the fermions that you have in the standard model. You do also have, so you basically say that the masses, the fact that, you know, the masses of these fermions breaks flavor symmetry of the standard model. You can also have lepton and baryon number, which are accidentally conserved. We don't enforce it. We don't put that in hand, like we don't put that as a requirement for the terms in there. But when you write down all the terms that we can for the standard model, according to these rules that I've written here, then you end up getting that lepton and baryon number, et cetera, preserved. Okay, so as I said, I want to talk about these gauge local symmetries, because that seems to dictate a lot of the particle content that we see and how we understand the interactions. So what is this? So imagine, so as an example, imagine that you had some scalar, okay, and it had some charge, let's call that E, under some U1 symmetry. Okay, so this is some hypothetical U1 symmetry that your Lagrangian has. So what that means is that this scalar that I call phi here, it can transform with this phase factor here, e to the I times E, which is this charge, times some local function, beta of x. Okay, that's what it means for the symmetry to be local, that this transformation here is some arbitrary function of, you know, the coordinate. So now the thing is that, you know, regardless of what the potential for this phi field is, the kinetic energy term corresponding, you know, for this phi term, for this phi field, is not invariant when you do this transformation, right? So if you look at this, right, the kinetic energy term is this d mu phi squared. You're taking the derivative of this phi, and when it transforms with this exponential here, which has a function of x, then the derivative will act on this beta as well. And when you do this, that means that you will necessarily get an additional term, which is going to have derivatives of this beta function, right? And so this term, this is not going to be invariant. You're going to, you know, you do this transformation on your Lagrangian, and you're going to get these additional terms, right? So the Lagrangian will have changed. So what do you do about that? Well, that means that actually you need to have this additional, well, you need to have something which basically cancels this addition, that, you know, this change due to this beta. So you need to have some other field, okay, which transforms in such a way that you get rid of these additional terms. So what you do is promote this derivative here, this partial derivative in your kinetic energy term, to what's called a covariant derivative, which we denote by this capital D. Okay, and what this capital D has is this partial derivative that you had previously, plus this additional term given by, you know, which is given by this A, okay, which is your gauge boson. And when you have this U1 transformation at the same time as, you know, phi transforms by this phase factor, the A transforms by a shift by the derivative of beta, okay? And so what happens is that now when you have this transformation happening, okay, so U1, you have this, the way phi transforms this way, you have A transforming this way, and the partial derivative is replaced by this, then in a few lines of algebra, you can show that in fact now the Lagrangian does remain invariant. So as I said, the presence, if you have a Lagrangian which has a local symmetry, a local gauge symmetry, so a transformation that leaves it invariant, that means that you need to have these gauge bosons present, okay? And not only that, but also because of the way they must be present in the kinetic energy term, it also precisely dictates what the interaction of these gauge bosons will be with whatever field, is charged under this symmetry. Okay. All right. So then again to the standard model. So as I said, it has this symmetry, SU3 color cross SU2 left cross U1 Y. Now the SU3 color refers to, that's the strong force. And that means that each one of the quarks that I showed you that interact with the strong force actually comes in these three colors, which we call red, green, and blue. And I want to emphasize it has nothing to do with what we call, actual color, regarding light. This is just a way to define three different charges that these things can have. And so each one of them, so for example, the up quark can have, these three different types of charges, and so on and so forth. And so they come in triplets, okay? That's why it's SU3. For the weak force, you basically have that there are pairs of fermions which transform together in a certain way, which leaves your Lagrangian invariant. And this U1Y is a hypercharge. So each of these different particles which have a Y hypercharge then can transform according to the example that I just gave you, which is a phase transformation. So now this means that you're going to have all of these gauge bosons which are present. So for SU3, that actually gives you 8 gluons, which I denote here by this capital G. And those are the mediators of the strong force. You have SU2, which will have 3 gauge bosons, which I call Wi, and this U1, which has 1 gauge boson. And these 3 forces basically have strengths corresponding to their couplings. Okay, and that's I denote them be G strong, G, and G prime. So and you'll see sometimes different notation, but this is mostly what's written there. Okay, so anyways, so that's what we understand broadly about the symmetry structure of the standard model. So going back to it, however, what we can note is that while the Lagrangian, the interactions, etc., that we wrote down for this model is minimal in the sense that we just write down basically the least amount of things, the least interactions that we can write down consistent with what we observe. But the actual structure of it, the content of it, the number of fermions is completely non-minimal, and if anything, looks completely unnatural, right? Why should there be these copies of these different fermions, which look basically they're the same as each other, except for the fact that they have wildly different masses. So in a sense, it's an arbitrary content. The masses are arbitrary. Those are, again, this is all built empirically, okay? And I will talk a little bit about this in a few minutes, but these different fermions also mix together in pretty much an arbitrary fashion. So I should also point out that the different rows that we have over here, so I told you the columns, each column is the same. And each row is also the same. So each column is the same, copies of each other, but each row has the same quantum numbers except for the masses. And this up here, we call them as up-type things, and these are down-type, and we have a similar thing for the leptons, and that has to do with their hypercharge assignments. But there's another thing. So apart from the fact that these the quarks come in 3 copies, right? They have the 3 different colors. These also have basically what we call either left-handed or right-handed. Any of these fermions can be that. And the reason why I'd written SU2 left is that only the fermions which are left-handed are the ones that feel the weak force, okay? The right-handed fermions do not. And so if you, well, maybe I didn't stress it enough, but when I was talking about the gauge bosons that have to be present, those also had to be massless, okay? So both fermion and gauge boson masses are forbidden by the symmetries that we just wrote down, this SU3 cross SU2 cross U1, all right? And well, that's a problem because clearly the fermions that I was just showing you, they have masses. And also the gauge bosons, the W and Z, as I told you already, they're massive, okay? And they're not small masses. The W and Z are like 80 and 90 GeV, okay? So something else has to be going on. And that's precisely where the Higgs mechanism comes in. And again, it is something that we kind of just write down because it's something that works, but we don't actually have an understanding of where it comes from, okay? So then the statement we make is whatever gives rise to fundamental particle masses has to break this electroweak symmetry, all right? So that's the Higgs mechanism. So what we're doing is that there has to be a spontaneous breakdown of this symmetry, all right? So this is what I wrote down initially, SU2 left cross U1Y, and that is actually broken down to what's called U1 EM, okay? That is your electromagnetic U1, okay? So the charges under U1 are what you normally think about as the electrical charge of whatever particles, okay? So how does that actually work? So I want to, again, give you a sort of hopefully a physical understanding of the process that happens. So you imagine that there is a scalar field, which is what we call the Higgs field. And this Higgs field acquires a non-zero value, which minimizes its energy. So the picture for that is given here. So you write down a potential, okay? So again, we're pulling this out of a hat, right? We write down the simplest thing that we can, which has a minimum which is not at zero, okay? So it has a minus phi squared and a lambda phi to the fourth, all right? And if you looked at what this looks like, this is sometimes called a Mexican hat potential. So you see this shape, okay? And now the zero of this potential would be at this point here, but that is clearly not the minimum of this potential. The field is going to roll to the minimum, right? To this point over here. And now this point has reduced symmetry, right? So this is, it has some vacuum expectation value, okay? So that's what we say when we say that the vacuum becomes a source of energy and hence a source of mass, right? So, but not only that, it costs energy for this field to fluctuate up and down in the radial direction now, okay? In this valley, okay? And that fluctuation is actually what we associate with the Higgs particle. But there's also symmetry that is left over. So if you look at this circle, right? Movement along the bottom of this valley, that does not cost energy. And that actually is a symmetry that still remains. And that is actually the residual symmetry of the system that's left over. And these modes, this movement, along this is what we call Goldstone modes, and will turn out to be the thing that become part of the W and Z gauge bosons and actually make them masses. But anyway, more generically, so you have this field, right, which fills all the vacuum. It's not empty, and it has now a non-zero expectation value. Okay, so everything that interacts with this background field then can gain mass. All right, so this is kind of a picture of that. So these crosses are supposed to be interactions with this background field that you have, and the more a field interacts with this background field, the more massive it's going to be. Okay, so basically the coupling of the fermions and the gauge bosons to this background field is what dictates their masses. So we know what, basically the mass of the Z and the W gauge bosons is given by the gauge coupling, the strength of the thing that I just told you about, times what's called the vacuum expectation value. And similarly, the fermions, all of them are going to be given, for example, some coupling constant here, which we generally call the Yukawa, times the vacuum expectation value. And what we know is this, the value of this V, from the fact that we know these different fermion and gauge boson masses. So we know that V is 246 GeV. Okay, so that's great. That's the Higgs mechanism. But how do we know that the scalar that we have, that we discovered at the LHC back in 2012, how do we know that it's actually the Higgs, the one that we're just talking about, that does this mechanism? So we have to start off with, well, how do scalars interact with gauge bosons? So as I told you when we were giving that example of the generic U1 symmetry for an arbitrary scalar, the coupling, the interaction of the gauge bosons with the scalar are dictated by the covariant derivative term, the kinetic energy term, and I've written that out here. Yeah. So now what you see is that when you expand this out, you're going to get a term which is going to be this one times this one, right? So it's going to have two A's and two phi's in there. And what that means is that there is an interaction between two A fields and two phi fields, okay? And the coupling strength is going to be given by E squared, all right? Now, that is true for any arbitrary scalar, all right? But what makes the Higgs special? Well, the thing that makes the Higgs special is that it is the thing which acquires this vacuum expectation value, right? So as I told you, what we call the Higgs particle is the fluctuation around this minimum. So your field phi is given by this H, which is the physical particle fluctuation, and this vacuum expectation value, right? This V, okay? So what that means is that if you replace phi by this, H plus V, you're going to get, interactions of these A's with the H, but also this constant term V. So when you have this 4-point interaction, two gauge bosons interacting with two phi's, you will also have one Higgs interacting with W and Z, and the proportionality between them is going to be given by this vacuum expectation value. And also, you're going to have, this connection between them is that both of these Higgs legs, right? I mean, we'll get the VEV, and that is what gives you the mass term for the W's and C's. And the thing is that we have actually observed this coupling, okay? And we know the mass. And so we know this proportionality between them, and we've seen that what we call the Higgs does in fact couple to the W and Z gauge bosons with basically the right strength that you would expect from this whole Higgs mechanism, this what we call the standard model like Higgs. So bottom line, at this point, it does look like the particle that we have looks very much like the standard model like Higgs. It behaves in the way that you would expect from this whole Higgs mechanism picture. And it does in fact generate the masses of all of the standard model particles that we see. So the plot that I show you here is the various coupling strengths versus the mass of different standard model particles. And it's actually one of the first plots that was given out by the LHC way back one. And it's still, however, one of my favorites. Just really cool that, right at the beginning, they were able to say that, look, this is the relationship that you have between the masses and the coupling of these things to the Higgs. Anyways, so now I want to switch gears just a little bit. I mentioned this before, that apart from the masses, there is this funny business of mixings. So what in the world am I talking about? So this is, I'm going to talk in particular about what are called quark mixing. And if you want to go look that up more, I'm talking about in particular what comes about as a CKM matrix. So what I write down here in the top here is the Yukawa interactions. So this is the interactions between various quarks and the Higgs field. So you remember I told you that all of the fermions come in either left or right-handed types. And the Higgs is this phi here. And that couples basically the left and right things, okay? And this Y is over here. These are some arbitrary Yukawa matrices that we don't know what they are, okay? But they're the ones that give you the interaction of the Higgs with these various fermions. Now this is the case. So here, this is the case for the quarks. So that's what these Q and D and Q and U are, and the leptons also. Now the thing is that we actually, this is written down where these Qs, the quarks, etc., in here are in the weak interaction basis, meaning that these are the things which have a defined quantum numbers under the weak force. But that doesn't necessarily correspond to the mass eigenstates, which are the things that we actually observe physically in the world, which have a state of definite mass, okay? And the thing is that doesn't matter for the Higgs interaction, because these actually end up that you can diagonalize these for the Higgs interactions, and you just get that the Higgs interacts with the mass for these things. But it turns out that it does show up in the weak interaction. And however, what shows up is the fact that you can have different rotations, the way you go from the weak to the eigenstate phase, the mass eigenstates, different rotations between the up type and the down type fermions. And you remember I showed you the rows of the standard model. One was the up type and the other one was the down type, and it had to do with the fact that they have different hypercharges. So now, so as I say here, these up and down, this U left and this D left here, there's some mixtures, which we don't know, some rotation, which goes from the weak to the mass eigenstate. And in the standard model, I mean, there is no way to extract what these rotations are independently. All we have is actually the product of these two things, okay? So the product of this, which I call BCKM, which is U left dagger, D left, this actually appears in the W interactions. Okay, and so you can interpret this, for example, as saying that your weak states are actually mixtures of, these are your mass eigenstates. Okay, so and this here I write down basically what happens, right? So you go from the weak eigenstate and you have to multiply by this V to go to your mass eigenstates, which are again the things that you actually observe physically in your lab, okay? Your propagating degrees of freedom. So bottom line, you don't know what these arbitrary Yukawa matrices are that govern the Higgs interaction with your fermions. But there can be some arbitrary rotation between the weak and the mass eigenstates. And we only have information about the product of how the up and the down type rotate. So this is in fact one of the I think great successes of the standard model is the CKM unitarity, because that's actually the only thing that we do know about what the structure of the CKM matrix has to be. Because these are rotations, it has to be unitary, okay? So V dagger V has to be equal to 1, all right? But we don't know, again, what these things independently are by themselves. And the components of these, this VCKM has been measured very precisely over a long period of time. And I won't go through in detail about how they do that, but the relevant point being that this is approximately a diagonal matrix. So if you look at the components here, they're almost, the diagonal elements are almost all exactly one, and you have small off-diagonal components, right? So what this means is that, you have small, you have mostly the weak eigenstate is mostly the mass eigenstate, but it has admixtures of the other ones. But also, interestingly, if you look at it, the first two generations seem to have a much larger mixing between them than they do with the third generation, right? This number is significantly smaller than this. And it raises the question that we want to go beyond the standard model. We want to understand where these patterns that we have just observed empirically, where do they originate from? Is there some bigger structure that dictates that? So we ask questions like, okay, is there something special going on from about the third generation from the CKM, or is this just related to, as I told you, this mass hierarchy that you have between the three generations? I mean, just from here, what I showed you here, there doesn't seem to be, there doesn't have to be, there is no explanation in the standard model for, where this comes from, okay? We just arbitrarily put this down. But again, things, which are puzzling, maybe points in the directions to things we would like to explore when trying to do beyond the standard model physics. Okay. So now, given all of this, I mean, at the LHC, since the Higgs has been discovered, there's been a huge program of precision Higgs physics. So there's been very many studies looking at how does the Higgs couple to all kinds of different particles, the production and the decays. And what I'm showing here is basically what you would the observations as compared to what you would expect from a completely standard model like Higgs boson. And this red line here basically denotes 1, right? So the ratio is 1, then this Higgs is completely what you would call a standard model like Higgs. So what, and of course, these things are different, various measurements in different channels here. So there's still, you can see there's still large uncertainties, right? Some of them are significantly larger than others, and there's some spread around this. But overall, it looks, pretty consistent with what you would expect from the standard model, okay? And of course, as you can imagine, there's, programs to continue these studies so that, we can narrow down these error bars in there to hone down, and if there is a deviation as compared to the standard model, or if these things all lay down completely on one. All right, so given all this, again, the goal is we want to try and understand what could be the bigger picture beyond the standard model. So, obviously we have been working on this for a long time, right? And there is a huge theory space of ideas out there. I mean, so this is just a schematic of the different types of models which try to address different questions or concerns you might have on about what could be going on. So there's, various SUSY models, there's, axions, extra dimensions, et cetera, But I am a great believer actually in the unknown. The space of models that we haven't thought of yet is pretty much infinite, right? So the way I see all of the different models, theory space that we have is that maybe there's, stuff that works really well, one particular thing that works really well in this type of model, and something that works really well here and something there. And that's kind of maybe giving you some ideas about what the fundamental end picture is going to look like, okay? So, you can think about, for example, questions about what's called fine tuning, like is, what we're seeing would be very unnatural in some way, in some type of model, right? And we are looking at low energy physics. But what may appear to be fine tuning, so we're looking at, the electroweak scales at LHC energies, etc. at this point here, which might appear to be fine tuned, may actually be a prediction, because we're not seeing what's on top here, right? And you can think about what's holding the structure together is actually some ultraviolet symmetries, which actually complete the picture of what we have, but we are not seeing that. Okay, so seeing various fine tunings or relationships that you have to have at low energy may guide you towards what could be happening up here. But also maybe they're accidental in some way, right? You're seeing this part again. That's because you're not seeing the glass. Okay, so there's some bigger structure that accidentally gives rise to the stuff that we're seeing. But now you probably do have, in the big picture, some connection between these two things, right? And what we see first, or how we understand things first, will very much depend on, well, what things are, what our experimental probes are, and what we discover first. So this is kind of a spiel to tell you to keep an open mind about what type of new physics we could have, which would be the extension of the Standard Model. So the way, again, I see it is, this is the picture of physics that we see around us, like some rubble of some stuff, right? We're looking to put together some sort of puzzle from observations around us. And what I feel like the state that we're at, so you see this rubble, is we're trying to pick up little pieces of things which seem to match together, and hope that if I can make these little piles, one here and one here and one here, then I would be able to get a global picture, a bigger picture of what things could actually have been. Okay, so with that, let's try to talk about, okay, fine. So how do we actually go beyond the Standard Model with the Higgs, with this whole idea about symmetries, etc., that I've talked about? So first off, the Standard Model Higgs is in fact a doublet of SU2. Okay, this SU2 left that I talked about. So doublet means it is a two-component field. Okay, so that's what it looks like. So that's the Standard Model field, and it has these two components. One of them is this charge thing, and the other one is this neutral component over here. And this here is the thing that we actually call the Higgs particle. Here is its vacuum expectation value. And I told you this is 246 GeV. We know this is 125 GeV from the LHC. These things here, this G plus minus and this G0, these are the Goldstone modes, the rolling modes that I told you about. And they actually get eaten, that's what we call it, say they get absorbed basically by the W and Z gauge boson to give them mass, okay? So this seems to work really well. So why would you think that we should have any more Higgses? Well, there's, a whole bunch of reasons you could think about that. There should be maybe more doublets, right? More scalars which look like this, which are weakly charged in the standard, but as we see in the Standard Model, in whatever extensions that you have. So as we talked about, the Higgs VEV generates the Standard Model fermion masses. But I've already mentioned that there's this huge hierarchy that you observe between like the first and third generation, right? I mean, maybe there are additional Higgses out there and they have different Higgs VEVs, and that's why we actually see the different masses, okay? This is actually what happens in, for example, SUSY models. And it turns out that SUSY requires that there be at least 2 Higgs doublets, okay? You could also imagine that there may be multiple extra dimensions and you get different Higgs doublets, which get different webs due to, different warpings in these extra dimension. So just to say that, there's reasons why it would make sense to think about having more than just the standard model like Higgs in your theory. So as, just as a case study, I'm going to talk about, consider models where you have now 2 Higgs doublets. Okay, so that's what's called this 2HDM. All right. But also, there's a possibility of what I called here dark Higgs, which is that you could have, scalars which don't have any electric, weak, or strong charge. So that would correspond to what you would call the standard model singlet. Okay, so it's not charged under any of the gauge groups of the standard model. It doesn't feel any of the standard model forces. Okay, and that's why we call it this S. Okay, capital S for a singlet. Why would we think that that might be a good idea? Well, I kept mentioning to you that there's this, mystery dark matter out there. We know very little about it, but we're pretty sure that it doesn't have any electric or strong charge. So maybe these singlets, these type of singlets, if they're around, they could be portals to dark matter. There's possibilities that singlets like this could be dark matter itself. Another thing, which I will not really touch on very much, but I think maybe you'll have that in some of the other lectures, is the question about the matter-antimatter asymmetry around us, which originates, we think, one of the hypotheses from what we call baryogenesis. I mean, the point is that clearly we see matter around us rather than nothing, yeah? And if there was exactly the same amount of matter and antimatter in the universe, it would have been all annihilated and we would have been left with nothing. That didn't happen. So that's this process of what's called baryogenesis. So as the idea is that as the universe cools down, the Higgs field develops a web. So this is, I don't know how well you can see this, but pictorially at high temperature, the Higgs potential basically was like a U, but as the universe cools down, it starts developing this little dip, okay? So for baryogenesis to happen, which is that you want to generate this matter-antimatter asymmetry, you need this phase transition when the field rolls from the 0 point to here to be first order, so kind of a strong interaction. So I kind of think of it as an explosive interaction. Okay, you need there to be a barrier which the field kind of tunnels through. Okay, but what happens if you just look at the standard model content is that you get this rollover, right? You never get a barrier between the 0 point and the minimum. You just kind of roll over from the 0 point to your web. However, if you have additional singlets in your theory that can perturb the Higgs potential so that in the evolution of this Higgs potential from the symmetric phase to this broken phase, that you develop this barrier. And so that's another reason why you could think about standard model singlets to be there in your BSM theory. So anyway, so just again, as a case study, we could consider, well, what kind of physics happens if you have additional Higgs doublets and singlets in your Higgs sector. And in particular, when we're adding stuff, we have to make sure that we are actually consistent with everything that we have observed so far. So, before we can go any further, you have to think about the fact that what I just told you about the experimental results, etc., is that what we see is very much what I call a standard model like Higgs boson, right? It has this right coupling to the W and Z gauge bosons, the fermions, etc. So how would that work if you actually had additional doublets or additional fields around? So So if you had two Higgs doublets, okay, that means you have two Higgses which interact weakly, right? So let's call them H1 and H2. And both of these, in principle, could acquire a vacuum expectation value. Well, if they interact weakly, then what we know is that the quadratic sum of these two has to be equal to 246 GeV, all right? So you have both H1 and H2, both can acquire vacuum expectation values. They're, the sum of them has to be 246 GeV, and you don't know what the ratio of these two, this angle, tangent beta, which is the ratio between them, what would be, okay? So first off, once you added an additional doublet, you would increase the particle content of your scalars, right? So you would actually have 5 physical Higgs bosons. You would have 2, which are CP even, which I call little h and capital H. And you would have 1, which is CP odd, which I call capital A. And you would also get charged Higgses, okay? So an example of this type of things happening is in supersymmetry. So as I told you earlier, in SUSY, you need to have at least 2 Higgs doublets, okay? And in that picture, what you have for 1 and 2 is that you have 1 Higgs which couples only to the up-type quarks, and you have the HD which couples only to the down-type quarks and the leptons. And you generally will have that these two guys here, the A and the H, capital H, those things are approximately mass degenerate. And the tangent beta is the ratio of the two VEVs of these corresponding Higgses. And this little H, I mean, one of these Higgses we obviously have to identify with the state that we've observed at the LHC. So this little H generally denotes that state that we see. Okay.
No, Shin, you have 4 more minutes.
Right.
Okay.
Okay. So now, how does that work with the fact that we actually do see a standard model like Higgs? Well, I can very suggestively write down these 2 combinations that of these H up and H down fields, okay, which are rotated basically by this some angle beta, okay? And I call this combination HSM for standard model and H non-SM, all right? Now, if you look at what the H up and H down are, there's V sine beta and V cosine beta. Because sine squared plus cosine squared is equal to 1, what you can simply see is that this state over here, this H standard model state, actually acquires all of the standard model value. And this particular combination of up and down has no vacuum expectation value, okay? So this is exactly what would look like, this guy would look like a standard model like Higgs. There's only 1 Higgs which actually acquires the vacuum expectation value. And this is the situation that we want to be living in. And so what we say is that whenever you're extending your theory by additional scalars, your little h, okay, the H125 that we've already observed, needs to be very similar to, close to this type of combination, okay? There can be additional states which have some other, component of it, because as I showed you experimentally, we don't know that we live exactly on that red line, right? There's some uncertainties. So there's some place for what we call misalignment, right? So in all of these pictures, this lighter guy, H, is, the 125 GeV standard model like Higgs. But the point is that you can have additional states. And these additional states don't have to be super heavy, okay? They can very well be around the electroweak scale, meaning a few hundred GeV. So this situation where, just 1 Higgs, this little h standard model, has completely all of the VEV is called alignment. And as I said, that would be perfect alignment. What we know experimentally is that we don't need to have perfect alignment, but we need to live very close to this particular scenario, okay? So the last thing I want to say today, and we'll pick up tomorrow, is that, so what's the difference between singlets versus doublets, right? So in this picture that I was showing about regarding this alignment thing, and what we're observing. I mean, if you had a singlet also, that would also mix in a similar way with the Higgs. It wouldn't have additional Higgs VEV, but it would share the 8 nanomodel VEV. But the way that you would look at experimentally when you were looking at the LHC, etc., is you would look at basically how do you produce these additional Higgses and how do they ultimately decay. So I'll talk about that also hopefully tomorrow. And also we have an experimental talk by Professor Sharma, I think on Wednesday, and I think that she will go through this in some detail. So I think that I will stop here for today, and we will pick up tomorrow. And I think we have about 10 minutes for questions. Yeah.
Thank you, Nosrin. So now, just as Professor Shah was saying, we have 10 minutes for questions.
PQ, I have some questions on the chat window, if you can see them.
Wait, I can see the chat now.
I've been going through the questions, so I can tell you the questions if you want.
Okay.
Yeah. So there are a couple of related questions from Divesh Jain and Chiranjeevi Dakal. So the question is, like, do all the particles in the standard model acquire their masses due to Higgs mechanism? And from Chiranjeevi, it's, if the Higgs mechanism is responsible for the masses acquired by the particles, how does the Higgs itself acquire its mass?
Okay, so first of all, so do all the particles in the standard model acquire mass due to the Higgs mechanism? The question is mostly yes, and the only exception is actually neutrinos, which I did not really talk about. So technically the neutrinos can in fact get their mass from the same mechanism as I described for everything, for all the other fermions, etc. But the difference is that the right-handed fermion, neutrino, is actually a standard model singlet, which means that it can actually just have what's called a Majorana mass by itself. And that's an open question, whether the neutrino gets its mass from a Higgs-Yukawa interaction, or if there is a Majorana mass term there. So that's the only exception to that. And then the other question was, where does the Higgs mass itself come from? So I will actually talk about that tomorrow. Well, it actually comes from the Higgs potential itself. Okay. So the mass of the Higgs scalar, you should think about as the energy it costs for it to oscillate at the bottom of the potential that I was showing you for the Higgs. So you have the Higgs field, right? The Higgs particle is the fluctuation around its minimum. The Higgs field permeates everything. So the fluctuation of the field around this point is what we call the Higgs particle. And it costs energy to go up and down. And what is that energy? Well, it's the second derivative of the potential over here. Okay, and that is exactly what corresponds to the Higgs mass. So I hope that answers that question.
Okay.
And then
we can wait for the follow-up if there's any. The other question is from Ayam Basnet. He's asking, are there any successful attempts to reconcile the standard model with dark matter? What effect would dark matter have in the symmetries that we take for granted in the standard model?
So no content of the particle content of the standard model can give you dark matter. Okay. There are many proposals of extensions to address that. So I think today there is one of the dark matter lectures right after this one, if I'm remembering correctly. So there's axions, there's WIMPs, etc., etc. Do we know what it is? Not yet. Whatever dark matter is, though, would have to respect the symmetries of the Standard Model. What that means is, hello?
I think it's just a background noise.
Okay. So what that means is that it has to respect the Standard Model symmetries, and in fact is not charged under the electric or the strong force. Well, I mean, that's a strong statement. It is a pretty strong statement. Dark matter can have weak interactions, but there are very strong constraints onto how strong, and when I say strong, I mean QCD, like the SU3 strong, and the charge that it can have. I don't remember the numbers off the top of my head, but it's some very large, very strong constraints, like 10 to the minus 10 E or something like that. Okay, that's the constraints on what the charge of dark matter could be. Okay. And then the next question is, does Higgs contribute to our understanding of gravity? So nowhere in this picture here is gravity. We don't actually know how to incorporate that because we don't have a consistent theory of gravity, quantum theory of gravity. Maybe the Higgs is connected to it in some way, but we don't know. Does the hat, then the next question from Anirban, does the hat shape of the potential change for large field values, as in including higher order terms? Isn't there different minima available at higher field values? Okay, so again, something I will address tomorrow. We have no idea. We really don't know very much about what the potential has to be. This form that I have written up here is literally pulled out of thin air. It's the simplest thing that could be written down, which would have this minimum shape over here, because really that's the only piece of information we have. We know the location of the minimum and we know the local curvature around that minimum. That's it. We don't know what happens at larger field values, etc. And that is actually an open question and very interesting one. How, what happens? Are there other minimums? And can be very relevant. In fact, when you're talking about this baryogenesis that I was talking about, is the evolution of the potential, from high temperatures to now, maybe another minimum forms first and you roll there and then, and then you tunnel to this one, etc. I mean, those are all very relevant questions and complete unknowns. All right, then the next question is what graviton may look like if we discover it, like its charge, mass, and spin. So the graviton, what we know of, what we think about is the mediator of gravity. And again, we don't really have a consistent way of being able to describe gravity in a quantum field theory, but you would think the graviton should be massless and not have any charge, and it should be spin 2. So that's and that's part of the reason why we can't. Yeah, we don't know how to write down. It's not a really normalizable theory. Okay, and then I think the last question: if we have a model that contains dark matter candidate plus one portal particle, should we need a dark Higgs to explain the masses of these new particles? You can or not. It depends on what type of dark matter candidate it is. I mean, if it is, for example, a Majorana particle, which means that it's a fermion, for example, which is its own antiparticle, then you can write down, then it can generically have a mass term. But at the same time, maybe there is another Higgs which controls the masses. Other Higgs, when I say Higgs, I mean something which requires a vacuum expectation value and does something similar to this, what happens in the standard model. We don't know. Those are all excellent questions and all possibilities that we have. And those are definitely
Okay.
that we play.
Yeah. So this is the last question here. So thank you, Nausheen, and let's move on to the second lecture of the day here. Dr. Nicholas Roth from CERN, who is going to lecture on dark matter.
Fantastic. Hello, everyone. Let me just try and share my screen. Are you able to see what I'm looking at?
Yes. Yeah.
Excellent. Okay, let me know when I can start. Ready anytime.
I think we can start.
Yes, we can start now. Yeah.
Excellent. Okay, thank you. Well, hello, everyone. And firstly, thank you to the organizers for the chance to present. And also thank you to all of you in the audience for coming along today. It's my great pleasure to have the chance to introduce to you the field of searching for the nature of dark matter using astrophysical observations today. And as I will hope to convey to you, I think there's a really exciting and active area of research which very well may determine what exactly this dark matter is made of in the next 10 to 20 years. Also, however, I appreciate that I'm going to be the first lecture in this school talking about dark matter. So let me spend a few minutes just reviewing for you what we know about dark matter at the moment, because we can use this as our bench, our underlying framework to look to where there's still a lot of work to be done. And I think in the modern context, our understanding of dark matter really dates back to a pioneering paper by Vera Rubin and Kent Ford from 1970. So what those authors were doing in that work was they were making observations of the Andromeda galaxy, which is what I'm showing you here at the center of the slide. It's our nearest neighbor in the universe. And they were trying to study essentially a very simple problem in the Andromeda galaxy, and that is to consider this system as sort of an upscaled version of the orbits of the planets in the solar system. So of course, famously, we understand that the orbits of those planets is controlled by our current theory of gravity. What these authors were trying to do was to understand how the same theory of gravity would operate in the Andromeda galaxy. In particular, they were looking at the orbit of objects around the galaxy here, and they were trying to see whether it matched up with our prediction. So what would that prediction be? Well, it's slightly more complicated than studying the orbit of the planets in the solar system. And that is because unlike in the solar system, where the majority of the mass is essentially just concentrated at the center, you can see by eye in the Andromeda galaxy that the mass is spread out. However, at some point you can see it's beginning to drop off. There's no more any additional mass getting out to the very large radii. And at those distances, we would expect that the orbital speed of the objects will begin to decrease because there's no more mass to compensate the fact that they're further away. And so eventually these orbital velocities should tend to zero. So there'll be some uncertainty, but if we were to put a theoretical prediction, it would look something like what I'm showing you on the slide here. Famously, however, what they observationally observed was not what we theoretically predicted. Instead, they found that the orbital speed of these objects that they were measuring plateaued to a non-zero constant value of about 200 kilometers a second, as you can see here. It seems that something very fundamental has gone wrong in our theoretical prediction here. We thought that all of the mass was dropping off. If we use our understanding of gravity, it seems like instead there's a huge amount of additional mass here if we want to try and make some sort of consistent picture of what's going on. So of course, the modern understanding of what's happening in the Andromeda galaxy is actually that there's a huge amount of additional mass, and just integrating over the mass that we can see by eye is the incorrect picture. There's this missing mass that we call dark matter that is required to make this, this data consistent with our theory. But now what we've had in the 50 years since the Rubin and Ford paper is many other observations where we also seem to need to have dark matter in there. But before I dive into explaining these in a little bit, let me just step back and really just emphasize what is the underlying principle that we're using to infer the existence of dark matter. And I don't mean to be patronizing here, but it's really quite a simple physical principle that we're relying on. And again, it goes back to thinking about the orbit of the planets in the solar system. So of course, our understanding of this is underpinned by our theory of gravity, and our knowledge of the our ability to understand the orbit of the Earth around the sun requires, for example, depends on properties like the distance of the Earth from the sun and also the mass of the sun fundamentally. So if we know these properties, we can then make predictions about the orbit of the Earth, or alternatively, if we measure the orbit of the Earth, we can try and infer properties like the mass of the sun. And why this is important is you could imagine a situation where, for example, we couldn't see the sun. Well, then if we really trusted our theory of gravity, just by looking at the orbit of the Earth, we would actually be able to infer properties like where the sun is located. It's somewhere near the center of our orbit here. And furthermore, we could also infer the mass of the sun because this will control the rotational speed of our orbit. And so this is exactly what's happening when we're making inferences about the existence of dark matter. We see objects orbiting, but we cannot see the object that they're orbiting around. However, we can still make quite quantitative predictions about where it is and what its mass is, just as we could in this situation here. So that's exactly what's going on when we look at these rotation curve measurements, which is what was happening in the Andromeda galaxy. If we look at larger collections of objects throughout the universe, for example, galaxy clusters, these are bound objects where each individual object in this system is a galaxy itself. It's like a solar system where each planet is a galaxy. These are massive objects. One famous example of a galaxy cluster is the so-called bullet cluster. And what we have here is we have two colliding galaxy clusters passing through each other. Why this is a very interesting observation is you might have said, well, the other key ingredient that went into our theoretical prediction for the Andromeda galaxy is our current theory of gravity. Maybe that's just wrong. And I think that's a very reasonable position or hypothesis to think about a priori. However, what that would mean is that the interaction strength between objects is changed at some sort of distance scale, for example, or acceleration scale. However, what happens in the bullet cluster is that we know where most of the mass we can see is in the bullet cluster. It's in gas. And we can measure where this is by using, for example, X-ray measurements. It heats up and emits in the X-ray. And we can see that in the red in the center of the image on the top right. Separately, however, we can ask where is all of the mass in this system? And we can measure that through, say, gravitational lensing, and that's shown in blue. And so we can see by eye very clearly that what's happened in the bullet cluster is that the majority of the mass that we can see in this object has been displaced from where the majority of the mass actually is. And this displacement makes it very hard to come up with a modified theory of gravity that could be consistent with this observation. Furthermore, we can study all of the structure throughout the universe, and this is generally known as the theory of structure formation. And at the moment, we have a very good theory that describes the distribution of structure throughout the universe, but fundamentally, it includes a dark matter ingredient. If you take that dark matter ingredient out, the great agreement that we have just vanishes. Finally, if we look to some of the larger scales we can see through in the universe in the form of the cosmic microwave background, once more, we have extremely detailed observations here of the CMB, and we have a theoretical prediction that agrees with this exquisitely. However, that theoretical prediction involves dark matter. Take that out and the agreement goes. So fundamentally, it seems that at all these different scales, we need some additional component of mass in the universe, and this is what we call dark matter. So just to give you like one more visual representation of what's going on here, if we just go back to this rotation curve example, you can see that if we didn't have dark matter by eye in a simulation, the galaxies would be moving at a much slower speed than what we actually find when we do the observations of these objects. Again, we really need dark matter to be there. So this has become such a quantitative field that we can do very precise measurements. And I can tell you now that actually we need around 84% of the mass in the universe to be in this dark substance we call dark matter. So all of the matter that we know makes up us and everything else we can see in the universe is vastly eclipsed by this dark matter. Furthermore, as a particle physicist, I'm coming into this problem and I'm telling you, well, whatever this dark matter is, it just has to be some new particle that we add to the standard model. And you might think about this for a moment and initially say, that sounds preposterous. I mean, you're telling me that the smallest scales where we see a deviation is at the size of galaxies, and you're telling me the solution to a galactic scale problem is at the subatomic level. But while this might initially seem preposterous, just to remind you, everything we can see in these objects here, we know to be made of particles. This is the great success of the atomic hypothesis. And so maybe it's then not so surprising that we can add in one or two more particles to the standard model and actually find a theory that is completely consistent with all of the observations that I've described to you here. So phrased this way, it seems like we really know a lot about dark matter. And the truth is that we do. But then we start thinking about dark matter as a particle. This is where I have to be honest and admit that at the moment, we're hideously ignorant as to exactly what that particle could be. So to quantify that statement somewhat, let's think about what even defines a particle. So one of the fundamental ingredients, as you were hearing about in the previous lecture, is its mass. And so you can ask, well, what is the mass of the dark matter particle? And the answer is we have almost no idea what this mass could be. It could exist over many, many, many orders of magnitude. So for example, what I'm showing you on the slide here is just a ruler of particle mass going from all the way from 10 to the minus 10 eV all the way up to 10 to the 28 eV. And just for reference, the mass of a proton is about 10 to the 9 electron volts. And so you can see roughly the range of the known particle masses in the standard model is this orange box at the top. And even if we extend this to include neutrinos, it goes down a little bit further. But what I'm showing you here for the range of dark matter masses is vastly larger than that. Dark matter could live anywhere in this space that I'm showing you. And actually, this is an incomplete subset of the full space of dark matter masses. At some point, it just becomes difficult to draw, so I'm restricting to this. So this is a fundamental challenge. Trying to determine exactly what dark matter is means we have to own up to the fact that we don't even know basic properties like its mass. But also this represents an opportunity. And the opportunity comes in the sense that for different particle masses, dark matter can behave very differently. And so we need to think carefully about how its mass could impact the way that it might show up in experiments. For example, it could be a particle not too different to the ones in the standard model, in which case we might expect it to have a mass near the masses of the other known particles in the standard model. It may be a much heavier particle, in which case individual states would be very rare, or instead it could be a very light particle. And when it's very light, actually dark matter will begin to behave like a wave. So it will behave very differently to how a lot of the particles we think of in terms of like electrons behave day to day. And so the different masses of the dark matter will then impact exactly how you want to search for it experimentally. So there is a huge program in physics of trying to determine what exactly the mass of this dark matter particle is, or more generally any of its additional properties. Many of these searches are operating here on Earth, which I would classify as terrestrial searches. There is a broad program that if dark matter has any interactions with the standard model, then maybe we could produce it at a collider like the LHC. So there's a broad program looking for any sort of signature events at the LHC for dark matter being produced there at all. Further, you could imagine that if dark matter interacts with the standard model, well then as dark matter particles pass through the Earth, they may occasionally bounce off one of our instruments. When they do that, they could leave a signal that we could hope to detect. And this is the broad program of direct detection. Furthermore, actually, if dark matter behaves like a wave, then maybe they'll leave some oscillating signal in our experiment that we're going to look for. Either way, if we build a sensitive enough instrument on the Earth, we could begin to tease out what exactly dark matter is. So these are very exciting directions in the search for dark matter, but they're not ones I'm going to be focusing on today. Instead, what I want to tell you about is how we can try and understand what particle dark matter is by looking back out into the universe, which is where we first discovered dark matter in the first place. So sometimes broadly, this field is called indirect detection, and this is often the way that I phrase it, but more generally, I'm just thinking about astrophysical searches for dark matter. Now, this in and of itself is an extremely broad field of research. Let me just mention to you 4 directions that we're thinking about searching for dark matter properties astrophysically. The first of these is what I would call classical indirect detection. And the underlying idea here is we take we gain some influence from what the properties of particles in the standard model can do. So for example, we know that the neutron isn't absolutely stable. It could occasionally decay. Or also we know that phenomena like electrons and positrons meeting to annihilate can occur. So we think, well, maybe dark matter particles could do something similar. Maybe they could decay, or maybe dark matter particles could annihilate. When they did this, they could decay or annihilate to standard model states like photons or neutrinos, which we can then go and search for. And this is the basic idea of indirect detection. And actually, I'll dive into this in a lot more detail in the rest of the lecture today. Additionally, though, we can think of other ways for trying to determine the dark matter properties. We know that there is dark matter all throughout the universe, and so there should be a lot of it passing through compact objects like stars. Some of that might get caught in stars and modify their properties. Alternatively, just the existence of a new particle in the standard model or beyond the standard model could modify the observable properties of stars or other compact objects like supernova or neutron stars. And there's a broad field of research trying to really tease out exactly what we can learn from this. Further, you can think about the structures of objects around the Milky Way to try and see if any of these tell us about the properties of dark matter. And so just to let you know, if you haven't heard already, I mean, just in the stuff that we can see, the baryonic matter, there is a very rich array of structure around our own Milky Way galaxy. My favorite example of this is the Sagittarius stream, which is what I'm depicting on the bottom left here. It's a stream of stars that we know goes out and wraps twice around the Milky Way. So if you haven't heard about this before, I really encourage you to look it up. It's just a beautiful object. And so this is something that we know exists in regular matter. The thought would be that also very complicated phase-space structures could exist in dark matter. And if we could tease this out in enough detail, then from measurements of that, we can try and distinguish between different particle theories because they make different predictions for what that phase-space structure could look like. So this is a very broad field of research that has really been accelerated by the recent launch of the Gaia satellite, is where a lot of the data for this field is coming from. Finally, I mentioned at the outset that we have really exquisite measurements of the cosmic microwave background. And because of this, if dark matter at all talks to the standard model, then it may actually modify the CMB. And this is something that we can look into in detail to see if there's any hints as to what dark matter might be from this. And so that's also a very active area of research. So again, just as a disclaimer, this is only a small subset of the different ways you could hope to determine the dark matter particle properties by looking out into the universe, but hopefully it gives you some taste for what type of ideas are underlying this field. To give you more of a sense though, what I want to do in the rest of the lecture today is just pick one of these topics and tell you a little bit about what the theoretical underpinnings of that field is, and then get to what is the cutting edge of that field, what are some active research areas, and where you can expect progress in the future. In order to do this, I just want to stick to one of the types of indirect detection I mentioned. I told you about the possibility that dark matter might decay, or alternatively dark matter might annihilate. Let me just stick for dark matter to decay for today's lecture. So again, just to make this concrete, I want to move to a quantitative picture here, but let me start somewhat qualitative. The fundamental idea here is this mystery that we originally identified in the Andromeda galaxy, well, it's resolved by the fact that there is a huge amount of additional particles in this galaxy that is this dark matter. So in particular, if we were to zoom in on one little box in the Andromeda galaxy and we had dark matter goggles, what we might expect to see for a certain dark matter mass is a gas of particles flying all over the place. Now, we don't have dark matter goggles, so we can't actually see this. However, in the scenario where dark matter can decay, we can get some hint on this because occasionally one of these particles would decay, and it may decay to a state that we can see, like, for example, an X-ray, and we can then go and look for this signal in X-ray satellites. Now, just to answer a question you might be thinking about, I mean, I told you earlier on that dark matter has to exist in the early universe, at least at the time of the CMB. And we also see it existing in the late universe because it modifies the observational properties of Andromeda. So if dark matter decays, it must do so extremely rarely because we need it to exist in the early and late universe. But that's okay. There are plenty of models you can write down where dark matter has a lifetime that is much longer than the age of the universe. And so this means that only some tiny fraction of dark matter would ever decay, but that's still enough potentially to give an observable signature. But how can we test these ideas quantitatively? I mean, I've given you some picture for what you can do here, but it's still very qualitative. And ultimately, if we want to make a detection of this, we need to have a very careful prediction for how many photons, for example, we should see at our telescopes if we are to see something consistent with dark matter. And this idea is quantified by the expression that I give on the lower left of the slide here, which tells you the dark matter flux, which is this object phi I've given you. And what the flux is it tells you how many photons should I see for a given detector area. The bigger detector I have, the more photons I should see, as a function of how long I observe. The longer I observe, the more photons I should see, and as a function of the size of the sky I'm looking at. This is the per steradian unit. And I tell you that this is given by this expression that I have on the slide here. There's a factor of the dark matter mass, m chi, its lifetime tau, but there's a bunch of other factors in here as well. So what I want to do is, rather than leave this a mystery, actually dive into this expression in detail and tell you exactly where this formula is coming from, so you have some intuition as to what is the underlying physics that controls what the dark matter signal should look like. Once we have an understanding of what all the expressions here are, we can begin to think about, well, where might we be able to make improvements in the future? And this is where the cutting edge research exists. So in detail, I just want to calculate for you this expression I've placed in an orange box. And to do this, I will break the calculation into two steps. In the first of these, so again, what this formula is telling me is how many photons, for example, should I see at my telescope coming from dark matter decaying all throughout the universe. So in the first step of the calculation, I'll just go to the location of where the dark matter particle is decaying and study the system of the dark matter decays to determine how many photons are at that location. And then in the second step, I will account for the fact that this process is happening all throughout the universe, integrate over the full volume of the universe to determine how many photons eventually arrive at our instrument and arrive at this expression in the orange box at the top. As I do so, I will only try and derive the simplest form of this expression, but I'll give you a hint or an idea as to where approximations are being made, because occasionally these approximations aren't valid, and in research you need to account for these modifications. Furthermore, just to say, I'm only focusing on dark matter decay here. However, if anybody who's particularly interested in understanding this in more detail, I really encourage you to go through the same exercise I'm about to do for dark matter decay for dark matter annihilation. The physics is somewhat similar, although there are interesting modifications, and doing so should really convince you that you understand what's going on here. I also see there are a couple of questions in the chat. I'm very happy to take those at the end, or if anyone has any questions in between, please don't hesitate to just interrupt and ask. Excellent. So now let's dive into the first part of this calculation, which is studying the system of dark matter decaying at the location where that's happening. We'll just forget about our telescope for a moment. So in order to study the evolution of a system of particles, it's generally the most careful way of doing this is to look at the Boltzmann equations. And so in particular, what we're going to do is study the Boltzmann equations for dark matter decaying to some state we want to see. I'll call that a photon, although you could make that a neutrino or something else, plus a whole bunch of other stuff. I'm just going to be completely agnostic as to whatever else dark matter might be decaying into, because we can never hope to see it at our telescope. We're only ever going to get one state out of this decay if it happens at astrophysical distances from us, many, many light years. So given this, I just need to understand what is the evolution of the number of photons that are being produced, because that's what I ultimately hope to see. So if I can write down the Boltzmann equations, there's an overly simplified version where you just have the Liouville operator on the left and the collision operator on the right. And I'm solving the Boltzmann equations as a function of the phase space distribution of the photons. This is this F gamma. And just as a reminder, this is the essentially telling you the probability of getting a photon with a particular momentum value and at a particular position. Is the phase space distribution of these photons. So let's tackle this equation side by side. I'll start with the left-hand side. And just to make my life easier for today, let's imagine we're only thinking about decays not too far away from us in the universe. This means that we can essentially ignore the real effects of cosmology, such that some of these photons will be redshifted on their path to us. But if we're looking at decays that are happening in, say, the Andromeda galaxy, these redshifting effects are certainly not important, so we can neglect them. And so if we're just looking in the local universe, the Liouville operator actually takes on a much simpler form. However, if you want to account for much more distant decays, then you'd need to modify this Liouville operator to account for that. I just won't be doing that today. Good, so this is particularly simple. We can rewrite the left-hand side as the energy of the photons multiplied by a time derivative of the phase space density. And so that's what I've placed at the top. However, ultimately, I don't want to know the phase space density of the photons. I want to know the number of photons, because that's how many I will see at my instrument. So let's rewrite this left-hand side in terms of the number of photons. And in order to do this, I have to integrate over the momenta that I'm uninterested in. It turns out to be more convenient to rewrite this instead of just an integral over the momenta, but an integral over a Lorentz invariant phase space, which is this d pi that I've put at the bottom here. And you can see the exact form of that on the inside. And because I've written this in terms of d pi, I need to add an extra factor of e and a factor of 2. That's where those are coming from. But then this tells me that if I integrate the Boltzmann equation by 2 times the integral of the Lorentz invariant phase space times energy, then I'll be able to rewrite this in terms of n gamma. Actually, scratch the energy, that term's already up the top. So doing this, I can write the expression as a time derivative of the number of photons in terms of some integral over the collision term. Okay, so we've made some progress here. The problem is, though, that now we have to turn to this collision term. And if anyone's dealt with Boltzmann equations before, they appreciate that this is usually where a lot of the mess lies. But let's dive into this nonetheless. So if you look this up in a textbook, for example, you'll find that the collision term takes on this somewhat complicated form that I'm showing you at the bottom here. Let's just break this down a little bit. So what I have at the start, these d pi's are integrals over the Lorentz invariant phase space of the various states involved. You might ask, well, hang on, what happened to the Lorentz invariant phase space of the photon? Well, just for the ease the notation here, for the point of just this calculation, I've placed the photon into the x. Remember I said that the dark matter decays to a photon plus anything else? Let me just put the photon into the anything else at the moment, or the x, so that I can simplify the notation. So that's where the photon phase space is hiding. Beyond this, you can see that we have a four momentum conserving delta function. This process better conserve energy and momentum. Next, we have an amplitude for the process. Fundamentally, what determines the probability of this dark matter particle decaying is quantum mechanics. And so this amplitude had to enter at some level. And then finally, we need to account for the fact that these states involved obey quantum statistics, which will vary depending upon whether they're bosons or fermions. And accounting for this gives this final term in the square brackets here. So in general, you need to account for all of these terms, and this is just something you have to work through. However, in many situations, there's a dramatic simplification to this expression that we can perform, and that occurs in the following way. It turns out that these phase-space distributions are dimensionless quantities, and so you can actually ask, are these phase spaces much larger than 1 or much less than 1? And it turns out in most applications, unless you're thinking about very high energy densities or very low energy states, the phase space distributions are much smaller than 1. So that means anytime I have 1 plus a phase space distribution, I can replace that with 1. Furthermore, anytime I have multiple phase space distributions multiplied together, that will always be smaller than any term where I have less. So if you think it through, in this approximation, actually the only term that will survive from the square brackets is f chi times 1. Everything else will be higher order. So this is a dramatic simplification, and it's not always true. There are cases in research where you actually need to account for the fact that f could be bigger than 1. An example I'm giving you in the reference at the bottom of the slide. However, in most applications, it is true. And if this is the case, then the collision term simplifies down to this form that I have here. So at this point, it's still a bit messy, but it's much dramatically simplified. And at this point, you can go and look up your quantum field theory textbook and check what is the expression for the decay rate of a particle. And you'll find that it involves many of the same ingredients: integrals over Lorentz invariant phase spaces, the amplitude squared, and also a momentum conserving delta function. In fact, by just staring at the definition and what we have here, you can convince yourself that what actually is on this right-hand side dramatically simplifies. It's just the number density of dark matter that's combining this f chi with this d pi chi, actually very similarly to what we did for the photons earlier on. And then the remaining expressions are just the decay rate, which controls the probability for this dark matter to decay at all. So we had to go into a bit of mess here, but ultimately what we find out is something very simple. And so we can rewrite the Boltzmann equations for the photon phase space as I've written it at the top here. Now that I've got the final answer, actually, you could have just guessed this at the outset. It's quite an intuitive expression. What it tells me is that the time variation for how many photons I have at the location where the dark matter is decaying depends on two things. It depends on how many dark matter particles are there. That makes sense. The more particles are there, the more likely I am to have one decay. And it also depends on the probability for those particles to decay. That is controlled by this gamma. So in some senses, you could have just written down the answer immediately. However, why I think it's useful to understand that how you can always go back to the Boltzmann equations if needed is if you're ever working in one of these scenarios where the approximations that I mentioned to you don't actually hold. Then maybe it's a bit more complicated to just write down the answer, but if you know where this comes from, you can do so systematically. We can also study the Boltzmann equations for the phase space distribution of other states involved. Another particle we care about is the dark matter. So if we go through the exact same exercise for the dark matter phase space distribution, we get this second equation I'm writing here. And this tells us that the time rate of change of the dark matter number density is depleted by these decays. This is this minus sign. So again, it's a very intuitive expression. The photons are being created and the dark matter is being depleted. However, the nice thing about this second expression is it just involves n chi on the left and right-hand side. So we can actually solve this differential equation. And we can write down that the dark matter number density as a function of time is given by some initial density multiplied by an exponential suppression. So this is exactly what you would have expected. It's just like in radioactive decay. If these states are decaying, then the number of them will be exponentially depleted. And so you can track this as a function of some known dark matter density throughout cosmic history. However, note here that there's a time here. So if we're making, for example, we're considering decays that are happening in the late universe, so the time is about 14 billion years, the question is, how does that compare to the lifetime of dark matter, which is essentially the inverse of this decay rate I've written here? And as I mentioned to you earlier on, to be consistent with observation, the dark matter lifetime has to be longer than the age of the universe. I mean, actually, the absolute bounds on that, it doesn't have to be much longer than the age of the universe. But in many of the models we consider, we usually assume it's much longer than the age of the universe, at least 10 or more orders of magnitude larger. And if that is the case, only some tiny fraction of dark matter has ever decayed. And so it's an excellent approximation to just assume that the number density isn't changing at all from the perspective of dark matter. So if we make this approximation, then we can substitute this unvarying constant value for dark matter into the first expression. Now what turns out to be convenient is that Well, we can't go out, unfortunately, and measure the number density of dark matter throughout the universe. That's something we don't have access to experimentally. What we do have access to is the influence this invisible dark matter has on other objects through its gravitational influence, which is controlled by the mass that it has. And so we can rewrite the number density in terms of the energy density if we divide out by a factor of the dark matter mass here. And why this is convenient is it's just a rewriting, but it allows us to write this in terms of something we can experimentally measure, which is the dark matter mass rho chi. So this is telling us the time rate of change of the photon number density. And it's because it's the number density, it's really the number of photons we have per time, per volume, and it's written in terms of these expressions here. Furthermore, we may want to be more specific when we're making predictions, rather than just telling our experimental colleagues how many photons should hit their telescope. It might also be useful to know what energy those photons are at. So we want to know our result differential in energy. And if we do this, we just need to account for the fact that the decay rate has the probability of producing particles varies as a function of the energy of those particles. And the way that we determine this is by computing a differential decay rate, which is just one of the basic things we often calculate in field theory. And so this is the expression if we want to account for the energy information also. Excellent. So as written, we can always just keep this expression written in terms of the differential decay rate. It just so happens in the field of indirect detection, this isn't what's done. Actually, we introduce some notation to get away from this differential decay rate, largely for historical reasons, but so that you're not confused when you're looking at the literature, let me just tell you what that notation is. What we do is we take our differential decay rate and we factor out the Born level or tree level decay rate. So, in principle, if you want to understand the probability for dark matter to decay to a photon and anything else, you need to do the all orders calculation. Of course, as a general principle, we can't do that. So what we usually do is we start out with some tree level, which is an approximation to the true result, and then perturbatively calculate corrections to this. So what we commonly do is just factor out the tree level decay rate and call everything else the spectrum. Furthermore, we make a little lie where we say that the actual decay rate for this process is the inverse Born decay rate. Again, of course, that's not exactly true, but it's usually true to a very good approximation. And so we can rewrite this decay rate as 1 over the lifetime multiplied by the higher order or the general complications beyond this, which is what is included in the this spectrum, as it is called, DNDE. Good, so this ends the first part of the calculation here, where again, what I wanted to do is just study this system of dark matter decaying at the location of where it's happening. And what we've now calculated is how many photons we get as a function of time, energy, and volume. And it's given in terms of these expressions on the right-hand side, some of which are defined quantities we had to introduce. Good, so now I want to go to the second step of the calculation. And in the second step, what we're going to do is account for the fact that this process can be happening all throughout the universe. And to determine the total number of photons I see at my instrument, I need to account for all of that. So again, the picture is there's many particles out there, and we want to know what distribution reaches our instrument near the Earth. So firstly, let's just deal with a very clear point here, and that is that let's imagine just one volume element to begin with and ask how many photons get from that to our telescope. Well, we have to contend with the fact that potentially this is happening many, many light years, potentially millions of light years away from our telescope. And by the time the photons there reach the location of the Earth, the distribution of them will be spread out over some enormous sphere that will have a surface area of 4 pi s squared, where s is the proper distance between our telescope and where these decays occurred. So this is just an irreducible dilution that we have from living in a three-dimensional universe. But then what we want to have is the largest detector we can to try and subtend as much of that surface area as possible so that we get the most number of photons. But irreducibly, sorry about the background noise there, irreducibly, what we have is that we're only going to get some fraction of this flux controlled by the size of our telescope divided by the sphere over which this flux has been diffused. So we just have to account for this. And this tells us that the photons we have differential with our detector area will be suppressed by this 4 pi s squared factor that I've said here. Now, this isn't the only way that photons don't reach us at our telescopes. It could be that they could interact with something along the propagation from the decay to the location of the Earth. This isn't something that I'll discuss today, but it's something that you occasionally do need to account for. And for example, in my own work, there have been some instances where this has come up, and you can see an example in the reference at the bottom of the slide. So now actually it's convenient. We're almost on the left-hand side of this expression here. I mean, the number of differentials is starting to explode. So it's sort of convenient to introduce some more notation. And actually we're basically at the point where we have the flux of the dark matter decay that I described to you earlier, this phi that I introduced. All that we're missing is a differential in the size of the area on the sky we're looking at. So if we just look at our result differential in this surface area, d omega, we can rewrite many of the differentials in terms of this phi. This is what we defined earlier. It's the number of photons per observation time, per detector area, per region of the sky we're looking at. I'm being a bit loose with the differentials on the right-hand side here. You can potentially imagine that this isn't exactly infinitesimal, or you can do it more precisely. I'm just not going through that, going to be that level of precision in today's talk. Okay, so again, this is the flux we would get from just one volume element out in the universe. And now we want to move this volume factor to the right-hand side and integrate over all the volumes we have. So I can, here in equations, I've just done exactly what I said in words. What's convenient next is to rewrite this volume integral in spherical coordinates, in which case I can rewrite the Jacobian, as you would know, as s squared ds, where s is an integral over the line of sight as I look out into the universe, and d omega is just the region of the celestial sphere I'm integrating over. And nicely, you find that this cancels the two terms on the denominator here. And all that it leaves me with is an integral over the dark matter density along the line of sight. Finally, if we take that expression and we integrate over all the energies that we're interested in looking at, we arrive at this expression I gave you in the orange box up here. So I appreciate this was a slightly involved derivation, but hopefully you have some more intuition for where the various terms are coming from. For example, what controls how many decays we get is an integral over the dark matter density, but you know that really that's a lie. It's not really controlled by the density, it's controlled by the energy density or mass density. It's controlled by the number of dark matter particles. And so because we've rewritten this in terms of something we can experimentally measure, we had to put this m chi factor out the front. That's where that's coming from. Next, you know what this spectrum now is. I mean, there's some confusion in the literature. Sometimes people get lost as to exactly how this is defined, but you can see that it can be exactly defined back in terms of this differential decay rate, which is something we can always calculate in field theory. Furthermore, you understand where the tau's come from. This is the inverse Born decay rate. And this 4 pi factor has emerged from the fact that the flux is being diffused out over a sphere of surface area of 4 pi s squared. So hopefully you have some impression as to where the various terms are coming from. So what I want to do now, having explained to you in detail where this expression comes from, is to say, well, now we know what the flux should be. Well, we haven't discovered dark matter yet, so there must still be work to do. And let me tell you about where that work is occurring in terms of this equation. Firstly, I mean, in some sense, one of the most important aspects of this work is on the experimental frontier. We haven't seen anything yet. So one way of hopefully getting towards this is to build bigger instruments and make longer observations, because by doing this, we can measure smaller and smaller fluxes and hopefully begin to see some emerging signal of dark matter. So let me tell you what's happening on the experimental front and where we expect to be in the next 10 to 20 years. Good, so I'm encapsulating that on this complicated plot here. Let me break it down for you. What I'm showing you here is just progress on experimental indirect detection for searches in photons. I'm only showing you photon energies on the x-axis. You can look in other channels like charged cosmic rays or neutrinos. I'm just not showing that here for simplicity. In particular, I'm just showing you some limited range of photon energies going from roughly X-rays, which is at about a keV or 10 to the minus 6 GeV, up to sort of the canonical gamma ray range, which is at around a GeV in green, going up to very high energy photons up at around a PeV. So that's what's on the x-axis. What I'm showing you on the y-axis is some metric for how good these different instruments are at measuring flux. It's a product of the collecting area, size of the telescope, the effective area, multiplied by how long they collect data. This is the observation time t. So you can think about this as sort of an analog of integrated luminosity in a collider sense. Maybe for some of you that gives you some more intuition. The integrated luminosity, if you multiply that by the cross-section for some new physics process, that tells you how many events of that process should occur in your data set. Similarly here, if I multiply this effective area times time, by my flux prediction for dark matter, that will tell me how many photons I expect to get in my detector from dark matter decay, for example. Okay, so having defined the various terms, let me tell you where we're at experimentally at the moment. You can see down in the X-ray, we have a suite of instruments that have been running for several decades now, in particular XMM Newton and Chandra. We have a bit of a dip in sensitivity at this very experimentally challenging medium energy gamma ray range at around the MeV scale. There's the flagship NASA instrument Fermi that was launched just over a decade ago that has collected fantastic data at this green region here. And then you can see that there's a huge jump in sensitivity as we go up to the higher energy, and we have instruments like Hawk and Hess. So in the next decade or two, there should be progress on many of the energy ranges here. Let me just tell you a subset of the instruments that will come online. You can see we're going to have even more progress. The rich get richer in some senses up at the higher end. We have LASSO and CTA that can give us dramatic improvements up here. And you can see we'll also have more modest improvements at the lower end. There'll be some progress on this very challenging MEV range. And also in the 2030s, we expect to launch the Athena satellite, which will be a new flagship X-ray instrument. But I think if you look at this plot, it really begs the question of why is it that the sensitivities are so much better at the high end than they are at the low end? To draw your attention to the fact that the y-axis here is logarithmic. So these instruments up here are much, much, much more sensitive than the ones down below. And actually, there's really a very simple physical principle that controls this. And that is the fact that these lower energy photons interact strongly with the atmosphere, and so they do not get to the surface of the Earth. If we build an X-ray detector on the surface of the Earth, we will not see astrophysical X-rays there. In order to detect these, we have to get above the atmosphere. So that means a satellite generally, or there are also some balloon-based experiments people have worked with. But as a general principle, putting things into space is complicated and challenging, as I'm sure anyone who's been following the JWST launch is well aware. And so fundamentally, we can't put very large instruments in space. Probably the best we can hope to do is about 1 meter squared. And then we can't wait thousands of years for them to collect data. At least I'm not interested in doing that. So the more realistic timescale for an instrument is maybe a decade or so. And so if we just multiply these two numbers, we find a value of about 10 to the 12.5 centimeters per second, which is a very hard value to get beyond for these lower energy photon instruments. It's pretty much a hard limit here. We still need to make improvements to get there, but it'll be very hard to go beyond that. However, as these photons get more and more energetic, eventually the interaction they have with the atmosphere will be so violent that they'll create a shower of particles that we can actually detect on the surface of the Earth. And this is exactly the way that Hawk, Hess, and in the future CTA and LASSO will detect these photons. And as soon as you can see something on the surface of the Earth, you can imagine building a detector that is much larger than 1 meter squared. And so that's why we get this huge improvement in sensitivity at higher energies. Something else I want to draw your attention to in this plot is the fact that while we're going to have very exciting progress in the future, at some energies, there's not a near-term plan to make improvements. And this is certainly the case, for example, for energies around the masses of the particles in the standard model, which is where actually we might have expected to see a signal from dark matter if it is one of these states that has a very similar mass to a particle in the standard model. So this tells us that Fermi is giving us some of the best data that we expect to have in the next 10 to 20 years. It really motivates trying to get as much out of this data set as we possibly can. And one really exciting aspect of that is that this data is fully publicly available. So if you have some new idea that previously had been overlooked for how we can get information about dark matter from this data, you don't need to convince an experimentalist to do the search. You can download the data yourself and actually do that yourself. And this is something that I do in my own research occasionally. So if you're interested in doing this, I refer you to this URL in pink at the top left of the slide, where you can actually go and just download the Fermi data. So that's what's happening on the experimental front. Let me now tell you about where there's room for theorists to make improvements in the search for indirect detection. And this comes on the right-hand side of the equation here. So really, it's these two integrals where theorists can make a lot of improvements in terms of trying to help experimentalists search for this. So firstly, you can see that this whole business is critically dependent upon how much dark matter there is along any line of sight I'm looking. And so what we would need to do is to have a very clear understanding of where the dark matter is throughout the universe so that we can optimize our searches to know where to look for this. I mean, more generally, there's a fundamental problem of how do you tease out any signal from some potentially challenging background? And this is a broader problem that I won't go into detail here. But let me just stick to this fundamental question of how can we use insights about where we know dark matter is throughout the universe in order to optimize our searches for the fact it might be decaying. And really just to hit this home, if you had taken my advice and gone and downloaded the Fermi data from the URL I presented to you earlier, when you loaded it up on your computer, you would get a plot that looks something like this here. So just to give you some intuition for what this is, of course, there can be gamma rays coming in from any direction on the sky. What I've done is taken the full celestial sphere and unwrapped it onto this projection plot here. It's like an image of the surface of the Earth on a 2D plane. It's technically a Mulvey projection. So what you can see immediately is that there are a lot of gamma rays coming throughout the sky. And so maybe you initially get very excited, but then what you see in the data is that they don't look anything like what we would expect a dark matter decay signal to appear. So we do not expect dark matter to cluster, for example, into flat spiral galaxies. However, this is roughly what the emission is correlated with. I can tell you that it's correlated with the plane of our own Milky Way. So instead, what we're actually seeing here is mostly conventional astrophysical emission of gamma rays. And then we need to think carefully, well, how are we going to find a signal of dark matter on top of this? This is just a background that we need to contend with. So let me tell you now one way that people have been thinking about in the literature where to look for signs of dark matter decay. So if you remember at the outset of the talk, I introduced to you these objects called galaxy clusters. These are objects where they're a bound system where each individual bound object is a galaxy itself. So these are massive objects. And because they're so massive, they're thought to harbor unbelievably enormous reservoirs of dark matter. This means there'll be many, many dark matter particles in these objects, which makes them a priori fantastic candidates to go and search for dark matter decay. Because if dark matter can decay at all, there should be many of the states in these objects decaying. So one of the nearest galaxy clusters we know about is the so-called Perseus cluster. So actually what people have proposed was, instead of potentially looking in the Andromeda galaxy for dark matter decay, although people have also looked in the Andromeda galaxy, maybe we should go and look in these galaxy clusters, and for instance, an object like the Perseus cluster. So why this turned out to be a very good suggestion is that in 2014, Ezra Bulbul and her collaborators found an anomaly when studying the Perseus cluster. And by an anomaly, I mean an emerging signal that may actually be a sign of dark matter decay. So what this was it was a line that they saw at roughly 3.5 keV. Here are some of the original data. In the best fit background model, I'm showing you in red, and you can see it dips below the data. And to make this up, they said that you needed some additional emission mechanism, which may be dark matter itself decaying. So if this is true, it's one of the defining discoveries of physics. It would really begin to tease out exactly what dark matter is made of. So of course, I think it's natural to be skeptical in this situation and to think, well, how else can we test the possibility that maybe this particle is, what we're seeing is actually particle dark matter? So this was a question that my collaborators and I tackled back in 2020. And I want to tell you about how we did this, because really it just revolves around thinking carefully about this integral over the dark matter density that is fundamental in the indirect detection expression. So I'll just run you through a back of the envelope calculation here. So firstly, I want to ask the question of, well, these authors have told us they've discovered a signal in Perseus. So if I want to determine where else I might want to look to see a signal, well, then I better know how bright Perseus is so I can compare it to anywhere else I might want to look to get some sort of fair comparison. So let's firstly calculate how bright we think Perseus should be. And as I said, the relevant quantity is an integral over how much dark matter there is in Perseus. This is this key part of the indirect detection expression. And also, if I'm looking over some region where the Perseus galaxy is, I don't want to just integrate over the line of sight. I need to integrate over some area element of the solid angle. And as it will turn out to make my life easier, instead of just calculating the total flux from that region, I'll calculate the average flux. And so I'm dividing by the solid angle, which is this omega inverse factor I have at the in the prefactor. Good, so it turns out for the Perseus cluster, even though it's a massive object, it's so far away that we can roughly approximate it as some distant point source. And it turns out if you just substitute in a point source into this integral here, you can evaluate it essentially analytically, and you find that the integral is given by, there's this prefactor I had, and then otherwise there's the mass of the cluster and then 1 over the distance squared. So again, this is intuitive. The more massive the cluster, the more dark matter there is to decay. So it makes sense that's controlling it. And then it's a distant object. So the flux that we receive is diffused by 1 over the distance squared. That's where that factor on the denominator is coming from. Now I can actually put in numbers and be quantitative. I know that the Perseus cluster is about 3 orders of magnitude more massive than the Milky Way. It's roughly 100 megaparsecs away. I'm being very rough here. And I know that the instruments we've been studying it at have a field of view of about 10 to the minus 4 steradian. So if I put these numbers together, I get a value of 10 to the 29 keV per centimeter squared. Now, I don't expect you to look at that number and go, aha, it's somewhat meaningless in the abstract, but I'm just going to keep this around because I'll do this calculation somewhere else, and then we'll compare these numbers. So again, the claim is that if we look at the Perseus cluster, we see additional photons that may be explained by dark matter decaying to give rise to them. So the question I want to ask is, well, if this is the case, it won't just be dark matter in the Perseus cluster that's doing this. We know dark matter is all throughout the universe. So is there some other object or place we can look for this signal to test whether or not this is really dark matter, or instead maybe it's something unique to the Perseus system, for instance? in order to motivate you, I've actually drawn this figure at the bottom of the slide somewhat suggestively. You can see that what we need to do is integrate from our location at the Earth, not at all to scale, out to the Perseus cluster in order to determine how much dark matter is there. But as we do so, we have to integrate through a whole lot of dark matter that we have locally. And this is the fact that we believe that the Milky Way exists in a dark matter halo, just as Rubin and Ford told us that Andromeda does. And so every time we look out into the universe, we have to look through some of the dark matter that's closer to home in the halo that we live in. So the question I want to ask is, well, how bright will the dark matter be from these column densities of our own Milky Way halo? So let's now compute this. So unfortunately, it's a bit harder of a calculation because we live in the halo. I can't use a distant point source approximation anymore. Really, to get an accurate answer here, you have to sit down and numerically integrate this expression. However, I can give you a rough order of magnitude estimate for what the column densities would be by just pinning the calculation to values that we know about the dark matter density in the Milky Way. So for instance, we know that there is roughly 1 proton mass worth of dark matter per centimeter cubed near the location of the Earth, or more accurately about 0.4 GeV per centimeter cubed. Furthermore, we believe that our theory tells us that, and observations as well, that the dark matter halo of the Milky Way should be very spherically symmetric. So that tells me that on the opposite location of the galactic center to us, there should also be a location where the dark matter density is about 0.4 GeV per centimeter cubed. So just to get a ballpark for the density, let me just imagine it has some constant value, and I'll just integrate the column density from us to this opposite point of the galactic center where it also has the same value. Now, I know that the distance from us to the galactic center is about 8 kiloparsec, where, as a reminder, a parsec is about 3 light years. And so I'm just being rough here. If I take that distance to be 20 kiloparsec, I can get an estimate for the column density by just multiplying these two numbers together. If you can convert GeV to keV, that's 10 to the 6, and a kiloparsec is about 3 by 10 to the 21 centimeters. Putting the numbers in, you get a value that's 2 by 10 to the 28 keV per centimeter squared. Now is for the aha moment, because if we compare these two numbers, they're not that different. Perseus is brighter, admittedly. However, what is profound, or what is the important point of this calculation here, is that there's only one Perseus cluster that we can go and study and look at these objects for. The claim here is that every column density in the Milky Way, or anywhere we look, there should potentially be a signal of this dark matter line. It just won't be only a factor of a few dimmer. So in any given observation, Perseus will be better to look at. But if we integrate over many different observations, we could potentially get a huge improvement from the fact that everywhere we look, we should have this. And here we can really draw on the fact that actually we've had X-ray instruments staring out into the universe for decades. And they haven't always been staring at the Perseus cluster. But anytime they've looked, they should have seen some dim signal of this line, and we can combine those data sets to see if there's some hint. So unfortunately, what we found when we did this analysis and put it together was no hint for dark matter decay. Here's just some representation of the data that we saw. These are these black crosses here. Our best fit background model, I'm showing you in the red curve. And if dark matter in the Milky Way had been decaying to these 3.5 keV photons, we should have seen something consistent with the red dashed line here. Now, in our paper, we did a careful statistical analysis, but using sort of a chi by eye, you can tell that it's not a very good fit to the data that we've observed. And so it doesn't appear that whatever this anomaly is in Perseus, it's coming from dark matter decay. But hopefully this is giving you some flavor for the sort of intuitions that can drive an improved understanding of how to search for dark matter. And actually, while in this section, I've been really focusing on sterile neutrino dark matter, this is the most likely candidate to explain this anomaly that emerged. Actually, it turns out that similar intuitions really underpin a lot of modern axion studies, because the axion also in many different ways can give rise to X-ray photons, and similar intuition to what I've told you about here is also relevant to axions. And I know you'll be hearing more about axions in the remainder of this school, so maybe something useful to keep in the back of your mind. Okay, so in the last couple of minutes, I just want to say very briefly about where the progress can be made on this other part of the right-hand side of the indirect ejection flux. And that is, where can we make improvements in our calculation of this spectra, which I've placed here. Because fundamentally, as I said, the way that we calculate the spectra is to do field theory calculations. So this is an area where you can imagine that theorists can have input. And there's various different ways you can think about doing this. I mean, if you have some new dark matter model you're interested in, you want to predict roughly what its lifetime should be as a function of your fundamental parameters, and also you want to know what the spectrum should be. And as soon as you have those, in principle, you can write down a prediction for what you should see at a telescope, and then either set a limit or hopefully motivate a search that makes a discovery. So let me tell you about where you can make some progress on this DND, or some of the underlying principles that go into this. So again, fundamentally, remember what's happening in this process is that we're studying dark matter decaying to something we hope to see at our instrument, which I call S, plus anything else that we will never hope to see. And in principle, S doesn't have to be a photon. It could be a neutrino. It could even be an anti-helium atom. It's just one state we want to look for. So then the general problem of calculating the indirect technospectrum is that we just want to calculate the differential decay rate where we factor out this Born decay rate, this gamma naught out the front, as mentioned earlier on. So how are we actually going to calculate these decay rates? Well, now we need to think about more generally about how we calculate energy injections in field theory more generally. And the basic idea is that usually we think that there's some Lagrangian interaction that our dark matter might have with the standard model that gets this whole process going. So you could imagine, for example, the dark matter might be able to decay to an electron and a positron, for instance, and then it's through this decay that eventually it seeds all of the states that we end up seeing. And just to hit home, if you decay to 2 states, that doesn't mean that that's what you end up seeing. For instance, if I decay to 2 quarks, these quarks carry color. The quarks will emit gluons. This whole process will continue to shower, and eventually these states will hadronize, and these hadrons will decay, and they will give me photons, neutrinos that I can look for example, coming from the pions. Even if I decay to E plus E minus, those electrons and positrons will also emit photons because they're also charged states. And again, so you'll need to account for that complication when you're thinking about the exact spectrum that you're looking for. Actually, if you think about it for a moment, the words that I'm saying come up a lot when you're describing the physics at a collider like the LHC. There, what you're doing is you have some energy injection into a hard process. In the dark matter case, the energy injection comes from the dark matter mass, but at a collider, it comes from the collision, like proton-proton. And then what we have is we have the outgoing hard collision. Those states shower, hadronize, the hadrons decay, and only after including all of those effects do we get an accurate description of what we see at the instrument. So actually motivated by this, a lot of work in a lot of results in the literature have been based upon just modifying the calculations we have for colliders, or the results we have for colliders, and using that for dark matter. It's actually not a particularly difficult thing to do. And actually, just to hit this home, even in a really extreme case where dark matter could only decay to neutrinos, these effects are still relevant. And you might think, well, how is that possible? Neutrinos don't radiate. Well, actually, they do. If you get to high enough energies, the neutrino is charged under one of the gauge groups of the standard model, the weak interaction. So just as, say, a quark can radiate gluons at high enough energies, a neutrino can radiate electroweak bosons. And so you need to account for this effect if you want to accurately determine what spectrum of states will potentially arrive at your instrument. So indeed, what people have done in the literature was they used, say, these LHC simulation softwares to determine, say, what is the real spectrum of dark matter decaying to neutrinos when you account for these radiative effects that I just mentioned are relevant. And so what I'm showing you here is a spectra calculated with Pythia. This is one of these simulation softwares that was used by one of the experimental collaborations. And so on the x-axis here, I'm showing you the energy of the states coming out in dimensionless units. This is x, I factored out the mass. And then essentially some measure of the number of states that you're getting in the spectra on the y-axis. This is the d and dx. And so in blue, I'm showing you the neutrino spectra, and in orange, the photon spectra that comes out of this process. And you can see the neutrino spectra is peaked at high energies, consistent with roughly this delta function picture you might have had in mind. But that isn't everything. There is some softer emission, and that is what you're seeing in this plot here. However, the question, just to give you a taste for where there's work to be done, that my collaborators and I were wondering recently is that, well, a lot of this field is using Pythia, and Pythia is a simulation software for the LHC. So that's optimized at electroweak or TeV energies. However, as I showed you earlier on, dark matter could be much heavier. It could be much, much heavier than the electroweak scale, easily going up to 10 to the 28 EV. So if this is the case, should we really trust a simulation software that was optimized for LHC energies up at these much higher energies? Or could there be missing physics that can rear its head? And the answer is there absolutely can. When we included these missing effects, we found results that were orders of magnitude larger, this is a logarithmic y-axis, than what people have been using previously. So these are important effects to include. So actually the details of how we included this with some careful aspects of field theory calculations that I can say more about if there's interest, but given the time, I won't dive into now. Instead, let me just show you one of the fun results that I was very satisfied with that came out of this calculation. So one specific dark matter spectra that you could imagine computing is, let's say dark matter decays to 2 quarks, let's just say B quarks to be specific. Well, then I can ask the question of, well, what is the photon spectrum that comes out of that? And this is something I'm showing you here for a dark matter mass at around the electroweak scale, in particular about a TeV. So this is something where I really would trust Pythia to do the calculation, because it's something where Pythia or the LHC is measured quite accurately. But now what I want to do is move to much higher dark matter masses. And in particular, I'll show you what happens to the spectrum as we go all the way up to the Planck scale, 10 to the 28 eV. And each time I'm going to move up 1 order of magnitude in dark matter mass. And I'm showing you how the spectrum evolves as we do this. And it's not just the case that you just generically get more and more emission. There's more interesting features to this. You can see in the intermediate stage, the spectrum moves down. At the lower end, it's moving up. At the higher end, it's moving up. And also the evolution is slowing. You can see that there's a bigger difference between the spectrum at a TeV and 10 TeV as compared to the Planck scale and 1 order of magnitude below this. And actually, there's a way of understanding this by seeing that there's an analogy between the equations we're solving and the diffusion equation. And that's a little bit cryptic here, but I think it's really exciting, and I'd be happy to say more about it if there's interest. If this is something, I mean, if ever in your own research, you're thinking about dark matter decay or annihilation, and you need to get spectra for very heavy dark matter masses, rather than ask you to reinvent the wheel, we made all our results publicly available. So if this is of interest to you at all, please go and have a play around on this GitHub. Okay, so that was the second example of where there's theoretical progress being made on this front. But just to step back, what I've really focused on today is just one aspect of the astrophysical search to try and understand dark matter. And again, this is just one facet of the broader program trying to figure out what the dark matter of our universe is. And I think that while we've been searching for decades at this point and haven't found anything yet, there's many reasons to be optimistic that one of these future instruments, either in indirect detection or elsewhere, or new insights on the theory side, could lead us to the discovery in the near future. So I think there's many exciting aspects of this physics to look forward to. And if you're all interested in it, I very much encourage you to get involved. Okay, let me leave it there. Thank you so much to all of you for your attention.
Thank you, Nick. So there are some questions in the chat box, so I can summarize it for you. So one particular question from IAM is, how do you know, like, how can we infer that the dark matter present as a clumps in the universe, or is it homogeneous throughout the universe?
Good. Well, I mean, again, it really goes back to its gravitational influence. So you can imagine that if instead of the sun in our solar system, we just had a plane of mass everywhere, the orbits of the planets would be dramatically different. The fact that the sun is a localized point at the center of the solar system really has an impact on what we see there. Again, even if we couldn't see the sun, we could make some inferences about where the mass is just based on the fact that all these objects seem to be orbiting around something. And the same thing is true in galaxies. By just doing detailed measurements of where we see these objects orbiting around, we can infer that it's not just a flat distribution everywhere, but it actually has structure to it. In fact, in a certain sense, we can be even more dramatic. So as you may be aware, through the theory of general relativity, even light is influenced by mass. It gets bent, its path of propagation gets perturbed by the presence of mass. So what we can actually do in systems is look at the bending of light according to the mass. And when we do this, we can, in some rough sense, make a map of where dark matter is in the universe. And from this, we see very much that it is not just uniform, but it is structured. Actually, in almost all of the different aspects I've told you about here, the clumping of dark matter is really critical. In the CMB, the fact that dark matter is clumping plays a really important role on what we see here. Again, if the dark matter was flat, the distribution of the CMB would be very, very different. So it's a fair question to ask, but again, just through its gravitational influence and thinking back, it's really an upscaled version of the orbits of the planets in the solar system. We can in detail understand that dark matter is very much clumped. It's a good question though, thanks.
Mm-hmm. Okay, thank you. Another question is, what can dark matter interact with, or is it possible that it is made out of more than one particle? From Durga.
Yeah, thanks for that question. So in general, dark matter could interact with essentially any of the states we know about in the standard model. In principle, all we can do at the moment is set limits on the interaction in general. We can't rule them out completely. So for example, the fact that we don't see it by eye tells us that it does not interact strongly with light, or it can't carry a very large charge in some senses. But that doesn't mean it can't interact with electromagnetism at all. To give you an example of this, the axion, and you'll probably hear more about this in the lecture on axions, one of our best hopes for discovering the axion is the fact that we think it should couple to electromagnetism. So it should have some interaction with electric and magnetic fields. So actually the way that we search for the axion primarily is we set up huge magnetic fields on the surface of the Earth and look for the axion interacting with them. So there's absolutely the possibility it could do this. More generally though, we could imagine it could interact with through any of the forces in the standard model. And so this is both a challenge and an opportunity. The challenge is the fact that there's so many possibilities makes it really hard to pin down initially where we should look. But the opportunity is that there's a lot of interesting searches that are yet to be done to try and cover all of this space. So that was the first part of the question that was asked. The second part was, could dark matter be more than one particle? The answer is absolutely yes. And let me give you sort of a dramatic example of this. We know that fundamental particles aren't everything in the states we know about. For example, the proton is a composite object. It's not a fundamental particle. It's made up of 3 fundamental quarks. And more generally, there are gluons in there that are binding it together. You could ask the question, well, could dark matter itself be a composite object? And the answer is absolutely yes. And there's many theories people write down where this could be the case. And in fact, actually, this is one of the best candidates we have for populating extremely heavy dark matter. So the very heavy end dark matter could be, and by very heavy, I mean this mass of the sun, so extremely heavy. Dark matter could be, for example, primordial black holes. But at energies that are well above, say, the Planck scale, but not yet getting to the level where you're at, like, say, the mass of objects like the Earth, one of the best candidates we have for dark matter is that it could be a composite object, a massive collection of many, many, many different states. And in the standard model, or in the periodic table, we know that we don't have fundamental atoms with thousands of states in them. And the reason for this is because of the electromagnetic interaction. If you put too many protons together, that introduces a force of repulsion that makes that system unstable. However, you could imagine, if you're just thinking generally, the dark matter may actually be a system where it's very similar to the standard model. It just doesn't have this U1 interaction. In that case, you can have clumps of objects coming together that get bigger and bigger and bigger and don't become unstable. And actually, they're sometimes called nuggets or blobs in the literature, can be very, very heavy dark matter, where dark matter is made up of a lot of stuff. So it's a very natural question that you asked, and the answer is absolutely yes. Dark matter could be made of many things.
Again, Ayam is asking, any comments on James Webb telescope's possibility for detecting dark matter signals? Decaying dark matter?
Yeah, I believe so. I mean, firstly, I guess actually this is an opportunity to say, I mean, one of the nice aspects of the searches here is that these instruments that I'm telling you about that are looking for dark matter, in most cases, their primary motivation wasn't to look for dark matter. Generally, the universe emits in many different wavelengths and in many different channels. I mean, as we now know, also in gravitational waves. And so astronomers and physicists broadly want to study the universe in as much detail as we can. But what we've realized, over the last couple of decades is that in these data sets, there actually could be hidden a dark matter signal. So it's somewhat serendipitous. So there is already some work underway. Sorry, if there was a question, please just repeat it, but I didn't hear that exactly. But just to say, there is this work already underway thinking about how James Webb could be used to look for dark matter. In particular, in the wavelength where it's sensitive, you could do something, sort of directly analogous to what I've already talked about, although I don't think generally the most exciting dark matter candidates we're thinking about would live there. But more generally, what James Webb will be useful for is it's going to give us much more detailed information about certain epochs in the history of the evolution of the universe. And if dark matter has certain properties, it might modify those. And it's through those that I think is probably where James Webb will have the most impact on dark matter searches. But I could be wrong. It's a new instrument. There could be new ideas that we haven't thought of yet. And so I think that's always an exciting part of a new instrument going up, and why it's so amazing that it actually has so far completely gone without a hitch. It's a very non-trivial process.
Okay, there are a few more questions. So what is the reason to take what is the reason to use the Boltzmann distribution in your Boltzmann equation?
Just to note, I never put in a specific distribution here. I mean, you can really account for the quantum statistics, the fact that these could be either fermions or bosons, which is what you would expect fundamentally. The Boltzmann equations are generically, anytime you have some sort of kinetic problem that you're looking to solve, where particles are moving backwards and forwards through some set of interactions, it's just the most general way of solving this. I didn't make any specific assumption about the phase-space distributions, I believe, when I was going through that. And again, just to emphasize, often what you can do is just jump to the answer. As I said at the end, the result you get down is very intuitive, but what's useful for thinking about this in terms of the Boltzmann equations is if you have to deal with some of these more complicated corrections, like the fact these states really do have quantum statistics, then it's sometimes helpful to go back to the Boltzmann equations to track exactly where the various factors are accounted for. Hopefully that answers your question, but please let me know if not.
And Tong Nguyen has, can you access Fermi data for specific sources like the galactic center or Jupiter Sun, something like that?
So in general, what the Fermi data is, I mean, there's a bit more than this, but ultimately it's just a list of photons that Fermi has collected over time. So when you get it, there's a list of the photon, if their best guess as to where it came from on the sky, the energy of the photon, and then some measurements of what time it was collected and the uncertainty on all those parameters. So ultimately, you just get a list of photons, you download all of that, it's a lot of photons, so you usually bin the data and you get something like the map I showed you earlier on. So I believe once you have that, of course, it's very easy to zoom in on specific sources like the galactic center, or, I mean, if you're looking at something like the sun, you need to account for the fact that the sun is moving through time. So, I mean, this is sometimes something that a problem that is given to junior graduate students to just check that they can pull the sun out of Fermi data or something like this so that you can account for this. But in principle, you can do that also. I'm not aware off the top of my head as to whether the Fermi data set has a catalog which just allows you to download a part of the data set around some object. They may, however, I just have never used that in my own research. But just to say, for example, Fermi is an all-sky instrument. It can see essentially the whole sky. It has a very large field of view. But in some other instruments, they're very much not the case. They only see some tiny pinhole of the sky. And this is usually the case for X-ray instruments like this XM Newton that I mentioned earlier on, which is actually where a lot of this 3.5 kV story played out. So in the case of these instruments, because they're not full sky, they just see tiny parts of the sky at any given point. They're usually the observations are made of given object. And so there you really can look up catalogs of observations in the galactic center or observations of this particular neutron star. It's usually framed in that specific sense. So there, the intuition you had for how you can look for things is very much on point.
Okay, thank you. One last question from Hein. I'm curious, there is any angular distribution that is related to dark matter spectrum? I'm not sure what he's referring to.
So I guess, I mean, just to say a couple of things, I mean, of course, as a function of position on the sky, that the spectrum will vary. And this goes back to the first question I was asked, because dark matter is clumped. I mean, if dark matter was just flat, I mean, still, when you do the integrals, you need to account for the fact that, I mean, in general, the clumping will give rise to an angular variation that you need to account for. So I guess one aspect of the question you're asking is, could the spectrum itself depend on where you're looking in the universe? Could there be an angular variation to the spectra? And in the expression I wrote down, I assume there wasn't. But if this is what you're asking about, you're really on point, because in some situations, those two may not factorize. And to give you some intuition, the question then is essentially, does the decay of dark matter have any dependence upon the environment in which it's sourced? And actually, this certainly can be the case. For instance, if you have dark matter decaying to very low energy photons, like say radio photons, we know we have a lot of these photons throughout the universe. And they're actually, the decay of this state can be stimulatedly enhanced, just like you have stimulated emission in, say, a laser. So the fact this means that in certain environments, the dark matter will decay more rapidly than it will in other environments. Then you really cannot factorize these various terms like I did previously. The lifetime actually depends upon where you're looking. And actually, there are cases in annihilation where the spectra itself can depend upon where you're looking. So in general, that is something you absolutely have to account for. It's just another one of the approximations that is hidden in this expression I gave you in the middle of the talk.
Okay, one last fun question now from Sriya. Why are you standing? Just curious, because it's the first time I'm speaking this in an online talk.
Oh, I am, I mean, maybe this is giving away too much. I'm standing at my desk at CERN, and I don't know if you can see this, but actually I've got a standing desk where I just have a couple of textbooks with my keyboard sitting on top of it. So it's a much less sophisticated setup than I'm hoping it looks from your side.
There are no books on your bookshelf. Yeah. Great.
I only recently arrived here. I might need about 2 or 3 decades to fill those bookcases up. Yeah.
Okay, so thanks, Nick, for a very exciting lecture, and let's thank all the lecturers this morning. Now Shane and Nick for wonderful lectures for the beginning of the school here, and
also the participants for engaging with the questions.
Let's thank the participants for asking also very interesting questions too. So
definitely, thanks everyone, really enjoyed it.
Thank you. Okay, so